Hello there, and welcome to Science for Sleep, where curiosity takes its time and science slows down just enough to drift alongside your thoughts. Tonight, we'll settle into one of the most unusual and fascinating regions ever discovered in the universe, a place so vast and so empty that astronomers call it one of the largest holes in existence. It's known as the Booty's Void, and despite the name suggesting absence, there is a great deal to explore. A hole in the universe may sound like a mistake, as though something went missing, but in reality it's a window into how the cosmos organises itself. Before we venture into this stretch of near nothing, I'd love to know, where are you listening from right now? Is it evening in your part of the world, or perhaps closer to morning? What time does it feel like for you as you lean into this moment? It's a fitting question, because while we'll be spending the night discussing emptiness, we'll also be circling around how we measure, describe, and make sense of it. And if you find these calm explorations useful, or simply pleasant to have playing in the background as you ease into sleep, it would mean a lot if you gave the video a like, or perhaps subscribed, because that helps this small corner of quiet science reach others who might be looking for the same kind of slow learning. Now, with that, let's begin moving toward the great space that sits like a hollow bubble in the map of the cosmos. The Booty's Void sits in the northern constellation of Bootes, which itself is a familiar shape to skywatchers, home to the bright orange star Arcturus. In that same general region of the sky, when astronomers set out to chart galaxies during the early 1980s, they expected to find the usual distribution: clusters of galaxies connected in filaments, separated by gaps but never truly vacant. Instead, they noticed a region stretching about 330 million light-years across, where galaxies were astonishingly sparse. It wasn't completely empty, but compared to the surrounding space it looked hollow. Later calculations suggested that if the void had the same average density of galaxies as the universe overall, it should contain something like 10,000 galaxies. Instead, careful observations revealed only a few dozen scattered inside, almost like specks of dust in a cavern. For physicists, this was more than a curiosity. It was a challenge to understand how the known laws of structure formation could leave such a gaping region of emptiness right in the middle of the cosmic web. To picture what makes this so remarkable, consider that most galaxies are arranged in something called large-scale structure. The universe on small scales may look chaotic, with stars orbiting in galaxies, galaxies orbiting in groups, and groups sometimes colliding. But step back far enough, and the pattern begins to resemble a three-dimensional web, with strands and walls of galaxies wrapping around hollow regions. These hollows are what cosmologists call voids. They form naturally because of how matter responds to tiny fluctuations in the early universe. Regions with slightly higher density attract more matter, growing into clusters and filaments, while regions with lower density gradually empty out, their matter flowing away into the denser zones. Over billions of years, this process exaggerates the difference between crowded areas and vacant ones, leaving behind the voids. The Booty's Void is extraordinary because of its size. Most voids measure tens of millions of light-years across, but Bootes stretches over 300 million, making it among the largest such underdense regions ever recorded. When physicists describe emptiness, they rarely mean it in the everyday sense of nothing at all. Even the Booty's Void contains dark matter, low-density gas, stray galaxies, and photons crossing through. What makes it striking is the absence of the expected crowding. In a region that vast, one would normally expect rich superclusters, knots of galaxies bound by gravity. Instead, what we see is almost silence in the map of light. It's as though the universe pressed pause on galaxy building there, leaving a cavern where others are crowded halls, and that absence itself becomes data. Astronomers first noticed the void while conducting redshift surveys. A redshift survey is essentially a three-dimensional map of where galaxies sit. Because the universe is expanding, galaxies farther away from us have their light stretched into longer, redder wavelengths. By measuring this shift in light, scientists can calculate how far the galaxies are, Plotting thousands of these distances in all directions reveals the grand-scale architecture of the cosmos. When the team in the early 1980s, led by Robert Kirshner and colleagues, plotted galaxies in booties, they found an enormous, nearly circular gap. At first, it seemed too large to be real, perhaps an error in the data. But repeated observations confirmed it. Later surveys with greater depth and precision kept revealing the same thing: a hollow space far larger than most voids. The size itself raises questions about probability. In our best cosmological models, voids form naturally. But the odds of such a large one appearing are low. That doesn't mean impossible. In a universe as large as ours, improbable events are expected to occur somewhere. But it does make the Boots void a kind of laboratory, a place to test whether our understanding of cosmic evolution is sufficient. Cosmological simulations, especially those based on the LCDM model, lambda cold dark matter, can reproduce voids, though something on the scale of booties pushes the edge of what is predicted. That tension makes it interesting. Either it's a rare but acceptable outlier, or it hints at subtler physics at work. Inside the booties void, the few galaxies that do exist are remarkably isolated. In the denser filaments of the cosmic web, galaxies are surrounded by neighbours, pulled and stretched by gravitational tides, and frequently interacting. In contrast, a galaxy inside booties may find itself alone across tens of millions of light-years. This solitude changes how it evolves. Galaxies in voids tend to be bluer, meaning they form stars more actively, and they sometimes hold onto their gas longer because there are fewer encounters stripping it away. Observing them helps astronomers see what galaxy evolution looks like in near isolation. These lonely systems remind us that emptiness is never complete. Even in the quietest corner of the universe, physics continues to act. Gas still cools, stars still ignite, and gravity still ties the pieces together, though on a gentler stage. For many listeners, the notion of a cosmic void may bring to mind the idea of absolute nothingness, but physicists see it differently. The Bootes void is not a hole in the sense of an absence of space. It is space itself, but with a much lower population of luminous matter. The vacuum there is similar to any other region, filled with virtual particles appearing and vanishing, threaded by dark matter that we cannot see directly. What distinguishes it is the lack of galaxies, those great beacons of stars. That makes it less visually rich, but physically it is still governed by the same equations, the same expansion, the same gravitational laws. In fact, the emptiness amplifies certain effects. For example, voids can contribute to something called the integrated Sachs-Wolf effect, a subtle change in the cosmic microwave background radiation caused by photons passing through underdense regions. Measuring such effects gives cosmologists one of the few ways to probe dark energy and the large-scale structure simultaneously. Thinking of voids like booties also changes how we interpret the cosmic web as a whole. The web is not just galaxies and clusters connected by filaments, it is equally the spaces between them. The voids give the structure its contrast. Without emptiness, there would be no filaments to stand out. The Bootes void demonstrates this in an extreme form. It shows how the absence of galaxies can be just as informative as their presence, revealing the forces that sculpt the universe on scales far beyond any human-made structure. And so, beginning with this vast emptiness, we can drift forward into deeper questions. How exactly do such voids emerge from the physics of the early universe? What role do dark matter and dark energy play in stretching them to such sizes? How do galaxies stranded within them survive, and what do they tell us about conditions when the cosmos was young? When astronomers first began trying to understand the large-scale arrangement of galaxies, they expected that the universe, when viewed from far enough away, would appear fairly uniform. After all, the night sky gives the impression of stars scattered in every direction, and early telescopes showed galaxies dotting the heavens like tiny clouds of light. But in the late 20th century, astronomers began to notice that this smooth picture wasn't quite right. Instead of being evenly spread, galaxies were arranged in patterns clumped into filaments, arcs and walls, leaving behind large gaps. The story of the Boots void begins during this period when astronomers were mapping the distribution of galaxies in greater detail than ever before. The key to this discovery was a tool called the redshift survey. To understand why, it helps to think about how we measure distances in the universe. For nearby objects like stars within our own galaxy, astronomers can use geometric methods, measuring parallax as Earth moves around the Sun. But for galaxies beyond our own, direct measurement isn't possible. Instead, scientists rely on redshift, the stretching of light caused by the expansion of the universe. The farther a galaxy is, the more its light is shifted toward longer, redder wavelengths. By carefully measuring this effect, astronomers can estimate how far away the galaxy lies. When thousands of galaxies are measured in this way, a three-dimensional map of their positions emerges. In the late 1970s and early 1980s, a group of astronomers led by Robert Kirshner, along with Augustus Oehmler, Paul Schechter, and Stephen Schechtman, began conducting a systematic survey of galaxies in the region of the constellation Bootes. Their goal was to fill in a portion of the cosmic map, one slice at a time, and see how galaxies were distributed on scales of hundreds of millions of light years. Each measurement was painstaking work. The light from a galaxy had to be collected, its spectrum dispersed, and the position of familiar absorption or emission lines identified, allowing the redshift to be calculated. With enough galaxies measured, a pattern began to form. What the team found was startling. Instead of galaxies spread across space in a relatively even way, there was a vast region with very few galaxies at all. When they plotted the data, the absence was unmistakable, a gap spanning hundreds of millions of light years across. At first, it was difficult to believe. Could it really be that the universe contained such an enormous stretch of near emptiness? Perhaps the survey had simply missed galaxies because of observational limits. Maybe dust or some selection effect had obscured the view. But as more data were gathered, the conclusion became harder to avoid. They had stumbled upon a void, and not just an ordinary one. It was far larger than anything then known. By 1981, the Bootes void was formally reported. Its diameter was estimated at about 330 million light-years, which immediately placed it among the largest structures of emptiness ever observed. To appreciate just how large that is, consider that our own Milky Way galaxy is about 100,000 light-years across. The Bootes void could swallow thousands of Milky Ways lined up in a row. Even compared to galaxy clusters, which span tens of millions of light-years, the Bootes void was in a different category altogether. It was as if a cosmic bubble had been carved out of the universe, leaving behind only a few lonely galaxies. For the astronomers who first published the discovery, the void was both thrilling and puzzling. According to cosmological models, voids were expected, but not of this magnitude. The early universe was seeded with tiny fluctuations in density, regions where matter was slightly more or less concentrated than average. Over time, gravity amplified those fluctuations, pulling matter into the denser regions and leaving the underdense regions to become emptier. This process should naturally create voids, but the Bootes void seemed too large to fit neatly into the predictions. Was it simply an extreme example of a rare event, or did it suggest something missing from the standard picture? The excitement grew as other astronomers confirmed the finding with independent data. Later surveys, with better instruments and more galaxies measured, continued to show the same structure. There was indeed a gigantic under-dense region in Bootes, and it was one of the most remarkable features of the cosmic web. Over time, as redshift surveys expanded, astronomers realized that voids were not isolated oddities. They were a fundamental part of how the universe is structured. Galaxies arrange themselves into a web-like pattern, with dense regions forming walls, clusters and filaments, and the spaces between them forming voids. but still, the Bootes void stood out for its sheer scale. To many scientists, the discovery of such a large void was an important piece of evidence supporting the idea that the universe has structure on scales far beyond what had been anticipated. Before these surveys, cosmology often assumed that on large enough scales, matter would smooth out, becoming uniform. What Bootes and other voids showed was that even on scales of hundreds of millions of light years, the universe retains a striking pattern, alternating between crowded and empty regions. This changed how physicists thought about the growth of structure, and it motivated new simulations to test whether the standard cosmological model could reproduce such features. One striking aspect of the discovery is how it shifted the way astronomers looked at the night sky. To the naked eye, the stars of Bootes appear as they always have, a constellation shaped like a herdsman leading his animals. But behind those familiar points of light lies a gap so immense that human words like emptiness or nothing seem almost too small. It took the patient accumulation of redshifts, carefully plotted on graphs, to reveal the hole in the universe. Without those data, it would remain invisible, hidden in plain sight. It's also important to recognize that the void is not a perfect sphere of nothing. Even within Bootes, a few galaxies exist, scattered sparsely across the volume. Roughly 60 galaxies have been identified inside, which may sound like many, but compared to the expected thousands, it is a profound underpopulation. This imbalance tells scientists something important. Voids are not completely barren, but they are regions where galaxy formation was suppressed, where matter flowed away into the surrounding filaments instead of condensing locally. The discovery of those isolated galaxies provided valuable clues about what it means to grow up in cosmic solitude. As surveys continued, the Bootes void became a touchstone for understanding how voids fit into the cosmic web. The discovery demonstrated the power of mapping the universe in 3 dimensions. 2-dimensional images of the sky can't show these structures because galaxies overlap along the line of sight. Only when distance is added to the picture does the architecture reveal itself. The Bootes void was one of the first dramatic examples of what could be learned by stepping back and seeing not just the stars, but the full scaffolding of the universe. For physicists, the void also raised interesting statistical questions. In a universe governed by random fluctuations seeded in the early Big Bang, how likely is it for a void of this magnitude to appear? Cosmological simulations suggest that while rare, such structures can occur, though their probability depends on the exact values of parameters like the amount of dark matter, the strength of dark energy, and the spectrum of initial fluctuations. The Bootes void therefore became a benchmark, a test for whether cosmological models could generate extreme features. If they couldn't, it might signal that the model was incomplete. In this way, a vast emptiness became a crucial probe of the physics of the universe. The discovery of the Bootes void is also a reminder of how science often advances. It wasn't a single eureka moment, but rather the accumulation of careful data. Each galaxy measured, each redshift determined, contributed a point on the cosmic map. When enough points were gathered, a pattern appeared, and the pattern challenged assumptions. This is how astronomy reveals the invisible, not through sudden revelations, but through steady work, patient observation, and the willingness to let the data speak. As the years passed, astronomers grew more comfortable with the idea of giant voids. Other large underdense regions have since been identified, such as the KBC void and the Eridanus supervoid, each with its own peculiarities. But the Bootes void retains its place as one of the first and most striking examples. It symbolizes the moment when scientists realized just how dramatic the universe's large-scale architecture can be. From the vantage point of Earth, the sky looks filled with stars. From the vantage point of cosmology, the universe is a patchwork of crowded regions and hollows, with Bootes representing one of the largest hollows of all. Reflecting on that discovery, it becomes clear that emptiness is not a mistake or a flaw in the universe. It is part of the design, a natural outcome of the way matter and gravity interact over cosmic time. The Bootes void is a place where galaxies are rare, but physics is still at work, sculpting the universe in silence. The recognition of that silence, revealed through redshifts and surveys, marked an important turning point in our understanding. And as we continue to map farther and deeper, the Bootes void remains not only a region of emptiness, but also a reminder of how vast the universe is, and how discoveries that at first seem like holes or gaps can in fact be openings into new knowledge. When scientists talk about emptiness on cosmic scales, they mean something very specific. The word itself can sound almost philosophical, as though we were talking about a true nothingness, a vacuum without content at all. But in physics, emptiness is always relative. The universe is never perfectly bare. Even in the darkest regions, photons pass through, dark matter exerts its pull, and the quantum vacuum itself fluctuates with virtual particles appearing and vanishing. So when astronomers speak of a void, they are really talking about a region that has a much lower density of galaxies compared to the cosmic average. To measure such an emptiness, they need to know not only how many galaxies are present, but also how many should be expected if the universe were smooth. The first step is counting galaxies, and to count galaxies you need reliable distances. As mentioned before, astronomers use redshift as the main tool for this. A galaxy's spectrum is measured, and the familiar fingerprints of atoms, hydrogen lines, calcium features, oxygen emission, are compared to laboratory standards. The shift in wavelength reveals the galaxy's recession speed, which thanks to the expansion of the universe can be turned into a distance. Plot thousands of these points in 3 dimensions and patterns emerge. Filaments, walls, and clusters appear where galaxies crowd together, and in between, the gaps become visible. But how do you quantify a gap? It's one thing to notice that a region looks sparse, and another to give it a physical measure. Cosmologists define something called density contrast. This is the difference between the density of matter in a region and the average density of the universe, divided by the average density. If the contrast is positive, the region is overdense, like a cluster. If it is negative, the region is underdense, like a void. A perfect vacuum would have a density contrast of -1, meaning no matter at all. Real voids are less extreme, but still dramatically negative compared to average. The Bootes void has a density contrast that is very low, almost approaching the limits of what is observed in the universe. Another way scientists measure emptiness is by comparing the number of galaxies to expectations. If the Bootes void were filled with the normal distribution of galaxies, it should contain something like 10,000 within its volume. Instead, only a few dozen have been confirmed. This shortfall gives a direct sense of how empty the region really is. The galaxies that do exist there seem to sit like islands in an ocean, far from any shore. Each one marks the survival of a system in conditions very different from the crowded environments of galaxy clusters. Measuring emptiness is not just about counting galaxies, though. It also requires mapping the underlying dark matter, because galaxies are only the luminous traces of a much larger invisible framework. Dark matter makes up most of the matter in the universe, and it dictates how galaxies are arranged. In simulations, voids appear naturally as dark matter flows out of underdense regions into overdense filaments. To measure this in reality, astronomers turn to techniques like gravitational lensing. Even in emptier regions, the mass of dark matter can bend the path of light ever so slightly. By studying these distortions across many galaxies, researchers can infer the distribution of mass, both visible and invisible. These measurements confirm that voids are not simply lacking in galaxies, they are genuinely underdense in matter as well. Another subtle probe of emptiness comes from the cosmic microwave background radiation, the afterglow of the Big Bang. Photons from the microwave background have been travelling for nearly 14 billion years, and along the way they pass through cosmic structures. When they travel through a void, they lose a small amount of energy due to the integrated Sachs-Wolf effect. The expansion of the void means the gravitational potential well changes as the photon moves through, leading to a tiny redshift. By stacking the signals of many voids, astronomers can detect these imprints offering an indirect way to confirm their presence and properties. To fully appreciate what it means to measure emptiness, imagine trying to map a city not by its buildings but by the spaces between them. You would first chart where the houses, roads and towers are, and then look at the leftover gaps. The larger the gap, the more striking it becomes. Now imagine doing this not on the scale of streets, but on scales of hundreds of millions of light years. The Bootes void becomes like an enormous park in the middle of a dense city, except instead of trees and grass, it is filled with near darkness, with only the occasional streetlight left standing. Quantifying the emptiness allows scientists to better understand the rules that govern cosmic architecture. Another important part of measuring voids is their shape. They are not always perfect spheres. In fact, most voids are irregular, stretched by the surrounding structures. Computer algorithms have been developed to identify and characterize voids in galaxy surveys. These algorithms often involve drawing boundaries where galaxy density drops below a threshold, then calculating the size, volume, and density contrast. For Bootes, the shape is roughly spherical, which made it stand out so clearly in the early surveys, but other voids can be more elongated or interconnected, forming complex networks of hollows. Measuring these shapes helps scientists compare the real universe to simulations, testing whether the standard model of cosmology can reproduce the observed distribution. As instruments improve, the ability to measure emptiness has grown. Early surveys relied on photographic plates and painstaking manual measurement. Today, automated telescopes and digital detectors can collect redshifts from millions of galaxies, producing maps of astonishing detail. The Sloan Digital Sky Survey, for example, has created three-dimensional maps covering vast portions of the sky, revealing not only Bootes but countless other voids. These maps show that emptiness is not a rare accident but a fundamental feature, filling about half the volume of the universe. The Bootes void, however, remains exceptional for its scale. Physicists are also interested in how voids evolve. Measuring their properties at different redshifts, different cosmic times, reveals how emptiness grows. Because the universe is expanding, voids naturally stretch and become larger. Matter flows out of them and accumulates in the surrounding walls, leaving the centres even emptier. By comparing voids at different distances, scientists can watch this process unfold over billions of years. This too requires careful measurement. The density contrast of voids, their average sizes, and their distribution as a function of redshift all provide clues to how cosmic structure has grown under the influence of gravity, dark matter, and dark energy. In this way, measuring emptiness is not about documenting nothing. It is about quantifying the distribution of matter, both luminous and dark, across the larger scales. The Bootes void is a striking example because its scale makes the measurement unambiguous. Even in early surveys with fewer galaxies, the absence was clear. Later measurements refined its dimensions and properties, confirming that it is indeed one of the largest known voids. The consistency across different methods, galaxy counts, lensing, cosmic microwave background imprints, all strengthens the picture. What is remarkable is how much physics is contained in such emptiness. The density contrast tells us about the growth of structure. The shape tells us about the surrounding filaments. The imprint on the cosmic microwave background tells us about the interplay between matter and dark energy. The presence of isolated galaxies tells us about how environments shape evolution. All of this emerges from measuring what at first looks like nothing at all. To many, this may seem counterintuitive. We're used to science focusing on objects, on what exists. But in cosmology, absence is just as important. Voids are not mistakes or oversights. They're expected outcomes of the same physics that builds clusters and filaments. Measuring them with care allows us to test whether our models of the universe hold true. If the voids were too large, too numerous, or too empty compared to predictions, it would signal a gap in our understanding. The Bootes void, by pushing the extreme, provides exactly that kind of test. It is also worth noting that measuring emptiness depends on human perspective and ingenuity. To the naked eye, the region of Bootes looks like any other patch of sky. Only with instruments sensitive enough to measure redshifts can the void be revealed. It is not visible directly. It emerges only in the data, in the statistics, in the careful tallying of galaxies and the recognition of where they are missing. This makes voids a reminder that much of the universe is hidden, not in darkness, but in absence. It is the patience of measurement that brings them to light. And so, the Bootes void continues to stand as a benchmark of emptiness. Measuring its size, its density contrast, its internal galaxies, and its subtle effects on background radiation all contribute to our growing understanding of the cosmic web. Far from being a simple whole, it is a complex structure whose very emptiness carries information. The act of measuring that emptiness has transformed it from a curiosity into a tool, one that physicists use to probe the deepest questions about how the universe formed and how it continues to evolve. When we talk about the Bootes void, the numbers that describe it are so large that they can almost slip past the mind without leaving an impression. Saying that it stretches about 330 million light-years across sounds precise, but it is difficult to grasp what that truly means. To make sense of its scale, it helps to walk slowly outward, beginning with the sizes we know well, and then extending step by step until the enormity of the void begins to settle in. The Milky Way, our own galaxy, is a good place to start. It measures roughly 100,000 light-years in diameter. If you could somehow travel at the speed of light, which no spacecraft can, it would still take 100,000 years to go from one end to the other. Inside the Milky Way are around 200 billion stars, countless clouds of gas, and the central supermassive black hole known as Sagittarius A. For us, this galaxy already feels impossibly vast. Now imagine placing 3,000 Milky Ways end to end in a line. That line would still not reach across the Bootes void. The void is more than 3,000 times larger than our galaxy. Next, consider the local group, which is the small cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 dwarf galaxies. The local group measures about 10 million light-years across. This means that the Bootes void could contain not just one local group, but more than 30 of them, stacked side by side with space still left over. Looking larger still, the Virgo cluster, our nearest large cluster of galaxies, spans about 15 million light-years across and contains more than 1,000 galaxies. The Bootes void could hold over 20 Virgos laid out next to each other, each with all its galaxies and hot gas. Even a supercluster like Laniakea, which is the massive structure that our local group belongs to, extends across about 500 million light-years. While that is larger than the Bootes void, it shows how close the void comes to matching the dimensions of the largest known bound structures in the universe. The Bootes void is not a minor feature tucked away in a corner of the cosmic map. It is a central hollow nearly as wide as some of the greatest walls and filaments. Comparisons like this are important because they show that the Bootes void is not simply large in human terms, it is large in cosmic terms. Astronomers often describe voids in terms of megaparsecs, with 1 megaparsec equal to about 3.26 million light-years. The Bootes void has a radius of about 160 megaparsecs. Most cosmic voids measure around 10 to 30 megaparsecs across. This means the Bootes void is an order of magnitude larger than what is usually seen. Its sheer volume makes it extraordinary. To put it into perspective, if you calculated the volume of the Bootes void, it would be on the order of 10 to the 17th cubic light-years, a number so vast that even when written down it hardly conveys meaning. But when compared to the number of galaxies expected within that space, about 10,000 versus the few dozen actually observed, the emptiness becomes clear. The scale also matters for how physicists model the universe. The standard cosmological model predicts that structures on the larger scales should be statistically distributed in a way that matches the random fluctuations from the early universe. Small fluctuations in density grow over time under gravity, forming filaments and voids. The size distribution of voids is one of the checks on these models. If voids were routinely as large as boots, it would be difficult to reconcile with the physics we think governs structure formation. The fact that Bootis exists, while rare, can still be explained, but its extreme size makes it an important case. It sits on the edge of the expected distribution, challenging scientists to ensure their simulations can produce something comparable. Another way to appreciate the size of the Boots void is to think about the time it would take to cross it. Imagine a photon of light entering one side of the void. Travelling at 300,000 kilometers per second, it would still need more than 300 million years to reach the other side. For reference, 300 million years ago on Earth, the supercontinent Pangaea was forming, and the earliest ancestors of reptiles were appearing. In the time it would take light to cross the Bootis void, the face of Earth has changed completely. Continents have drifted, mountains have risen and eroded, species have appeared and gone extinct. Yet for the photon, that entire sweep of history is just the duration of its journey across the void. This timescale helps bring the size of the void into perspective. It is not just large in distance, but in time as well. There is also the question of how it compares to the overall size of the observable universe. The universe we can see extends about 93 billion light-years across. That makes the Bootis void only a small fraction of the total, but still one of the largest coherent features within it. The void occupies a volume so large that if you were to select a random region of the universe the size of Bootis, chances are you would find it far more filled with galaxies. This rarity is what makes the void striking. It is not that the universe is mostly empty, but that this particular emptiness is extreme. From a practical standpoint, the size of the Boots void affects how we study it. Because it spans such a vast region, astronomers cannot capture it with a single telescope view. Instead, they rely on wide surveys that sweep across large portions of the sky, building up data piece by piece. This makes mapping such structures a multi-decade effort, with each generation of telescopes adding more detail. The early discovery of the void was possible only because the survey covered enough galaxies to reveal the absence. With modern instruments, the picture is more complete, showing the void as part of a larger network of voids and filaments, but still standing out as unusually large. The size of the Bootis void also has implications for the galaxies inside it. A galaxy drifting in such a space is far removed from its neighbours. While galaxies and clusters may interact, collide or merge, galaxies inside the void evolve more slowly. Their star formation histories, gas content, and overall structure are influenced by their isolation. Studying these galaxies is difficult because they are faint and far apart, but when measured, they show differences that help astronomers understand the role environment plays in galaxy evolution. The scale of the void is thus not only a feature of space but also a laboratory condition, setting the stage for a different kind of cosmic development. When thinking about the Bootis void, it is easy to focus only on the absence of galaxies, but the size itself makes it more than just an empty spot. It is comparable in scale to some of the largest structures we know. The Sloan Great Wall, one of the largest galaxy walls ever observed, stretches about 1.4 billion light-years, larger than the Bootis void, but both belong in the same category of extreme structures. The Bootis void is not a minor gap but a major feature of the cosmic landscape, standing alongside superclusters and walls as part of the grand architecture. This scale also helps explain why the void captures imagination. On human scales, emptiness is easy to dismiss. A room without furniture is empty, but it is still a room. A field without trees is empty, but still part of the land. The Boots void, however, is emptiness on such a scale that it rivals the largest concentrations of matter. It reminds us that the cosmic web is balanced not only by what is present, but by what is absent. Without voids of this size, the filaments and clusters would not have their contrast. The Boots void highlights this balance by being one of the most dramatic examples. In cosmological terms, the Boots void also serves as a marker of what we mean by large-scale structure. On small scales, galaxies form stars, merge, and evolve. On intermediate scales, they group into clusters. On scales of hundreds of millions of light-years, they form superclusters and voids. The Boots void defines this upper limit of structure, showing that the universe has features that extend far beyond what individual galaxies can reveal. The scale of Boots is the scale of the cosmic web itself, the scale at which the universe's architecture becomes visible. So when we say that the Boots void is 330 million light-years across, we are not only giving a number, we are pointing to one of the most extreme examples of how matter organizes under the laws of physics. We are comparing it to galaxies, groups, clusters, and superclusters, and finding that it sits near the top of the scale. We are recognizing that its size makes it both rare and valuable as a test of cosmological models. And we are acknowledging that its vastness is difficult to fully imagine, requiring comparisons and time spans just to begin to grasp. The Boots void is vast enough to be measured against the universe itself, rare enough to be statistically significant, and empty enough to stand out in any map. Its scale ensures that it remains a feature not just of astronomy, but of physics, influencing how we model the growth of structure, the flow of matter, and the balance of emptiness and presence. When astronomers first began to notice the Boots void, it wasn't through a telescope image that looked empty, or a patch of sky that showed a black circle. To the naked eye, and even through powerful telescopes, the region looks just as rich in stars as any other. What revealed the void was not an image, but a measurement, repeated thousands of times and plotted in 3 dimensions. That measurement was the redshift of galaxies. Understanding how such surveys work is essential to grasping why the Boots void was noticed in the first place, and why redshift surveys remain one of the most powerful tools in cosmology. Redshift is the stretching of light caused by the expansion of the universe. As galaxies move away from us with the overall flow of cosmic expansion, the wavelengths of the photons they emit become longer. This effect shifts the familiar lines in a spectrum toward the red end. The greater the shift, the faster the galaxy is receding, and the more distant it is. In this way, redshift acts like a cosmic ruler, turning spectra into distances. The principle was first discovered by Vesto Slipher in the early 20th century, who noticed that many galaxies had spectra displaced toward the red. Later, Edwin Hubble connected these redshifts with distance, showing that the universe is expanding. From that point forward, measuring redshifts became central to cosmology. In practice, a redshift survey is straightforward in concept but labour-intensive in execution. Astronomers select a region of the sky, identify thousands of galaxies and measure their spectra. Each galaxy requires careful observation. The spectrum must be dispersed with a prism or grating, recorded and analysed for the positions of key absorption or emission lines. Hydrogen, for example, leaves a series of lines at known wavelengths. If those lines appear shifted, the amount of shift can be calculated. The redshift is then converted to a distance using the Hubble law, corrected for details like the exact cosmological parameters. Once enough galaxies are measured, their positions can be plotted not just in 2 dimensions, the familiar map of the sky, but in 3. The right ascension and declination provide the directions, and the redshift provides the distance. When all the points are placed together, the map reveals the large-scale structure. Instead of a random distribution, patterns emerge. Galaxies form filaments, arcs, and sheets, with large hollow spaces in between. It was in such a survey that the Boots void was first revealed. The surveys of the late 1970s and early 1980s that uncovered Boots were modest compared to today's efforts, but they were groundbreaking at the time. Astronomers had to work with limited instruments, photographic plates, and early detectors. Each galaxy took valuable observing time. Still, by systematically covering the region of Boots, They gathered enough data to see the whole emerge. When the galaxies were plotted, the absence was unmistakable. There was a vast region where galaxies were expected, and almost none appeared. Modern redshift surveys have extended this approach to millions of galaxies. The Sloan Digital Sky Survey, for example, has mapped large portions of the sky with automated instruments, producing detailed three-dimensional maps of the universe. In these maps, voids appear naturally as underdense regions, and Bootes stands out as one of the largest. The surveys show that the universe on the largest scales is a cosmic web. Galaxies line up in filaments that intersect in clusters, while voids occupy the spaces between. Redshift surveys turned what once seemed like a smooth distribution into a structured architecture, and they continue to refine that picture. The technique is not without challenges. One complication is peculiar velocities, the local motions of galaxies on top of the general expansion. A galaxy inside a cluster may move relative to the cluster center by hundreds of kilometers per second. These motions distort the redshift, making galaxies appear stretched along the line of sight in redshift space. In survey maps, this produces features called fingers of God, where clusters look elongated. Astronomers must account for these distortions to correctly interpret voids and filaments. Another effect, called the Kaiser effect, compresses structures along the line of sight due to coherent motions. Understanding these distortions is part of the science of redshift surveys, and correcting for them allows voids like Bootes to be measured more accurately. Another challenge comes from observational limits. Galaxies become faint at great distances, and surveys are always incomplete. Not every galaxy is measured, so the maps are only samples. Sophisticated statistical methods are used to fill in the gaps and ensure that voids are not simply artifacts of missing data. The Bootes void has been confirmed across multiple surveys, which increases confidence that it is real. The more complete the surveys become, the clearer the void appears. One of the key reasons redshift surveys are so powerful is that they allow cosmologists to compare observation with theory. Numerical simulations of cosmic structure formation begin with conditions shortly after the Big Bang, seeded with small fluctuations. Under gravity, matter clumps into filaments and leaves voids. The size and distribution of those voids depend on cosmological parameters, such as the density of dark matter and the properties of dark energy. By measuring real voids through redshift surveys, physicists can test whether the simulations match reality. Bootes, being so large, is a critical case. If simulations could not reproduce voids of that size, it would suggest something was missing in the model. The process of creating a redshift survey is also a reminder of how much effort goes into mapping the universe. Each point in a void map represents hours of observation, careful calibration, and data analysis. The maps are not just images, they are constructed from the spectra of galaxies spread across the sky. When all the points are gathered, the patterns appear. For Bootes, the pattern was an absence, a hollow bubble that would never be visible in an ordinary photograph. Only through the collective data of hundreds of galaxies could the void be seen. The importance of redshift surveys extends beyond identifying voids. They also reveal the largest coherent structures in the universe, such as galaxy walls and superclusters. The discovery of the Sloan Great Wall, for instance, came from redshift data. The same maps that showed Bootes as a void also showed the surrounding filaments that border it. Together, the filaments and voids create the cosmic web. Without redshift surveys, this structure would remain hidden. The night sky alone gives no hint of it. For cosmology, redshift surveys also provide one of the main tools for measuring the distribution of matter on the largest scales. The clustering of galaxies as a function of scale, known as the two-point correlation function, is measured from these surveys. Voids contribute to this function as well, since they represent the scales at which galaxies are unlikely to be found. By analysing the statistics of the maps, scientists learn not just about where galaxies are, but about the underlying physics that put them there. Redshift surveys have become increasingly ambitious. Early surveys covered thousands of galaxies. Modern ones cover millions. Future surveys, such as those conducted by the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, will map tens of millions of galaxies with unprecedented precision. These efforts will not only refine the measurement of voids like Bootis, but also test fundamental physics, such as the nature of dark energy and the geometry of the universe. The Bootis void will continue to be part of this broader context, an extreme case among many, reminding scientists how large and empty the universe can be. One of the subtle but important aspects of redshift surveys is that they measure the universe in slices. A telescope can observe only a limited portion of the sky at a time. By systematically observing slice after slice, the survey builds up a three-dimensional wedge of the universe. Bootis was discovered in one of these slices, where the absence of galaxies across a wide range of redshifts made the void clear. Later surveys filled in the surrounding regions, confirming that the void was not a narrow gap, but a genuine bubble extending hundreds of millions of light years. To appreciate what a redshift survey reveals, it helps to imagine standing inside the data. If you were surrounded by points representing galaxies, you would see filaments stretching off in arcs, clusters shining as knots, and in the direction of Boots, a vast cavity with only a few lonely points inside. That absence is not just an empty patch on a photograph, but a region where the data points themselves are missing. The map becomes a three-dimensional portrait of presence and absence, matter and void. This is why the Bootis void could only be discovered through redshift surveys. No photograph, no matter how deep, could reveal it. Only by knowing distances could astronomers see that there was a bubble in space. The technique turned flat images of galaxies into three-dimensional structures, and in doing so it revealed the universe's hidden architecture. The Bootis void is one of the most dramatic examples of what redshift surveys can uncover, but it is also just one part of the larger web. When astronomers looked at the results of the first redshift surveys, what struck them most was not only that there were voids like Boots, but also how galaxies seemed to follow an underlying pattern. They were not scattered randomly like grains of sand on a table. Instead, they lined up in great arcs, walls and filaments, separated by vast hollows. This arrangement is now known as the cosmic web, a network of structures stretching across the observable universe, with galaxies and clusters marking its nodes and strands. To understand why the Boots void is such an extreme case, it is helpful to look closely at how galaxies are normally distributed, and how this distribution shapes the universe as a whole. Galaxies form where matter gathers under gravity. In the early universe, about 380,000 years after the Big Bang, matter and radiation decoupled, leaving behind tiny density fluctuations imprinted on the cosmic microwave background. These fluctuations were only one part in 100,000 different from the average, barely perceptible. Yet, over billions of years, gravity amplified them. Regions that were slightly denser pulled in more matter, growing denser still, while less dense regions lost material. The outcome of this slow amplification was the formation of clusters, filaments, and voids. Galaxies, as visible objects of stars and gas, act as tracers of this invisible structure. Their distribution reflects where dark matter and baryons have settled. On small scales, galaxies group into pairs, groups, and clusters. Our Milky Way is part of a pair with the Andromeda Galaxy, bound together and destined to merge in a few billion years. Together with smaller galaxies like the Magellanic Clouds and dozens of dwarfs, they form the Local Group. Groups like this are common, typically a few million light-years across, bound by gravity, with galaxies orbiting one another. Larger still are clusters, such as the Virgo cluster, with thousands of galaxies confined in a volume tens of millions of light-years across. These systems are so dense that galaxies often collide, merge, and strip gas from each other. The evolution of galaxies and clusters is shaped by their proximity, by the hot gas filling the cluster, and by the tidal forces of neighbours. On larger scales, clusters themselves link into superclusters. Our local group in the Virgo cluster are part of the Laniakea supercluster, which extends for over 500 million light-years. Within these superclusters, galaxies are not spread evenly, but form elongated structures called filaments. Filaments are like the veins of the cosmic web, channeling matter along their length, connecting clusters and superclusters. Between the filaments lie voids, the underdense regions that define the network. The Bootes void is a particularly large example of such an underdense region. To understand why it is remarkable, consider the average separation between galaxies. In the universe as a whole, galaxies are spaced about a few million light-years apart. Inside clusters, that separation shrinks dramatically, with galaxies often within a few 100,000 light-years of one another. Inside voids, the separation increases. In Bootes, the few galaxies that do exist may be tens of millions of light-years from their nearest neighbours, living in near isolation. The contrast is extreme. Where clusters are crowded cities, Bootes is a desert with only a few scattered oases. The distribution of galaxies is not just a matter of where they happen to be. It tells us about the underlying physics, simulations of the universe, starting from the initial fluctuations seen in the cosmic microwave background, reproduce the web-like pattern of galaxy distribution. Dark matter plays a crucial role. It provides the gravitational framework on which gas can cool and form stars. Without dark matter, the fluctuations would not have grown enough to form the structures we see today. Galaxies trace the peaks and strands of this dark matter distribution, while voids trace the troughs. Measuring where galaxies are, therefore, is a way of measuring the hidden structure of the cosmos. When astronomers map galaxies on scales of hundreds of millions of light-years, they find that the distribution looks remarkably like a sponge or foam, with filaments as the walls and voids as the bubbles. Bootes is one of the largest bubbles, a cavity where galaxies are scarce. It is not entirely disconnected from the rest of the web. The boundaries of the Bootes void are lined with filaments and clusters, forming a rough spherical shell. These boundaries are like the ridges of foam, where matter has collected. Inside, however, there is little. This arrangement makes the void striking in surveys, because the surrounding walls highlight the emptiness within. One of the interesting aspects of galaxy distribution is that it is scale-dependent. On small scales, the distribution appears clumpy, with galaxies gathered into clusters. On intermediate scales, filaments and voids dominate. On the larger scales, hundreds of millions of light-years across, the distribution begins to look more homogeneous, matching the cosmological principle that the universe is uniform when averaged over very large distances. Bootes sits in the range where structure is most pronounced. It is large enough to be considered part of the large-scale pattern, yet still distinct enough to stand out. Its sheer size pushes the limits of what voids can be, making it important for testing whether the observed distribution agrees with theory. The distribution of galaxies also influences how light and matter move. Gravity pulls galaxies toward overdense regions, so the filaments grow richer while voids grow emptier. Over cosmic time, galaxies stream out of voids and into filaments. This flow of matter is predicted by simulations and confirmed by observations of peculiar velocities. In Bootes, the underdensity is so extreme that galaxies on the edges are likely drifting outward, leaving the interior even more sparse. This dynamic process means that the distribution of galaxies is not static. It evolves, with voids expanding and filaments tightening. The Bootes void we see today is the product of billions of years of this evolution. The sparse distribution of galaxies inside Bootes also raises questions about how those galaxies formed. Did they originate within the void itself, condensing from small clumps of matter, or were they drawn in from elsewhere? Observations suggest that void galaxies are often smaller, bluer, and more actively forming stars compared to galaxies in denser regions. Their isolation protects their gas from being stripped, allowing them to continue forming stars longer. In this way, the distribution of galaxies shapes their properties. The Butter's void is not just empty space. It is an environment with unique conditions, and the few galaxies inside it are shaped by those conditions. Another way to quantify galaxy distribution is through statistical tools like the two-point correlation function, which measures how likely galaxies are to be found at a given separation compared to a random distribution. This function shows that galaxies are strongly clustered on small scales, but less so on larger scales. Voids like boots are the other side of this clustering. They represent the separations where galaxies are less likely to be found. In this sense, the Butter's void is not an anomaly but part of the statistical pattern of galaxy distribution. What makes it special is its size and depth, pushing the distribution to one of its extremes. It is also important to recognize that galaxy distribution is not uniform across different types of galaxies. Bright, massive galaxies tend to cluster more strongly than faint dwarfs. Elliptical galaxies are more common in dense clusters, while spiral galaxies are more common in less crowded regions. In voids, the galaxies that do appear are often late-type spirals, with ongoing star formation. The Butter's void, with its sparse population, provides a natural laboratory to test these trends. By comparing the properties of void galaxies to those in filaments, astronomers can learn how environment shapes evolution. The large-scale distribution of galaxies also provides insight into the role of dark energy. As the universe expands, voids grow. The rate at which they expand depends on the balance between gravity, pulling matter into filaments, and dark energy, accelerating the expansion of space itself. Measuring voids like Butter's helps constrain these forces. The distribution of galaxies mapped through redshift surveys becomes a tool for probing fundamental physics. The Butter's void, being so large, is particularly sensitive to these effects, making it valuable for cosmological studies. From a broader perspective, the distribution of galaxies in the universe is one of the most striking pieces of evidence for structure on the larger scales. To think that galaxies, each containing billions of stars, are themselves just points in a vast pattern is humbling. The Butter's void emphasizes this point by showing what happens when those points are absent. The surrounding filaments gain significance by contrast, their richness highlighted by the emptiness next to them. The distribution is not uniform, and that unevenness is what gives the universe its character. As mapping continues, more details of the cosmic web emerge. New surveys with larger telescopes and more sensitive detectors are revealing the distribution of galaxies at greater depths and across wider regions. The Butter's void remains a benchmark, a reminder that even in a universe filled with hundreds of billions of galaxies, there are still regions where galaxies are almost completely missing. The distribution tells us where matter has gone, how it has clumped, and how it has left behind voids. It is a story written not in light but in the spaces between lights. When astronomers first measured the Butter's void and compared it to what theories predicted, it became clear that something more than ordinary matter was shaping such vast emptiness. Gas, stars, and galaxies are only the luminous surface of a much deeper structure. Underneath them lies a hidden network made almost entirely of material that does not shine. This is dark matter, the invisible component of the universe that outweighs all the stars and galaxies we can see. To understand why a void like Butter's exists, and why galaxies arrange themselves in walls and filaments around it, we have to look at the framework built by dark matter. The evidence for dark matter began long before anyone thought seriously about cosmic voids. In the 1930s, Fritz Zwicky studied the motions of galaxies in the Coma cluster and found that they were moving too fast to be held together by the visible mass alone. Something unseen had to be providing extra gravity. Decades later, Vera Rubin measured the rotation curves of spiral galaxies and confirmed the same puzzle. Stars at the edges were orbiting too quickly to be explained by the mass of luminous matter. Again, some invisible component had to be present. These lines of evidence accumulated, and today it is widely accepted that about 85% of the matter in the universe is dark matter. dark matter does not emit or absorb light, but it interacts gravitationally. It is this gravity that sculpts the large-scale structure. In the early universe, when matter was nearly uniform, dark matter began clumping first. Because it does not interact with radiation the way normal matter does, it could start forming structures earlier. These clumps became the gravitational seeds into which gas later fell, forming stars and galaxies. Without dark matter, the small fluctuations in density we see imprinted on the cosmic microwave background would not have been enough to grow into the cosmic web we observe today. When cosmologists run simulations of structure formation, they begin with the density fluctuations measured in the microwave background and let dark matter evolve under gravity. The result, after billions of years of simulated time, is a web of filaments and voids. Galaxies form along the filaments at the nodes where matter is concentrated, leaving behind underdense regions in between. These simulations reproduce the distribution of galaxies remarkably well. They also show that voids like booties are not anomalies but natural outcomes of the dark matter framework. The booties void, then, is not simply a place where galaxies are missing. It is a place where dark matter itself is less dense. Galaxies follow the dark matter, so where the underlying framework is empty, galaxies are rare. This makes voids particularly valuable for testing our understanding of dark matter. If dark matter were distributed differently, or if it behaved differently under gravity, the sizes and shapes of voids would change. By measuring voids, scientists can indirectly measure properties of dark matter. One key feature of dark matter is that it forms halos. Every galaxy, including our Milky Way, sits inside a massive halo of dark matter. The visible disk of stars and gas is only a small part of the total mass. These halos extend far beyond the luminous parts of galaxies, and they interact with one another, merging to form larger halos. In dense regions, halos are numerous and overlap, leading to clusters and filaments. In voids, halos are sparse and isolated. The few galaxies in booties exist because a few halos happen to form there, but the overall density is far below average. Another important concept is bias. Galaxies do not trace dark matter perfectly. They are biased tracers. The efficiency with which galaxies form inside halos depends on many factors, such as the amount of gas available, the environment, and feedback from stars and black holes. In voids, the bias means that galaxies are even rarer compared to the underlying dark matter distribution. The Boötes void may therefore look emptier in terms of galaxies than it is in terms of total mass, but both are still far below cosmic average. Dark matter also determines how voids evolve over time. As the universe expands, matter flows out of underdense regions and into overdense ones. This process stretches the voids, making them larger and emptier. In simulations, voids expand like bubbles in rising bread dough, their boundaries becoming sharper as filaments grow denser. The Boötes void we see today is the result of billions of years of this flow, guided by the invisible pull of dark matter. Its current size reflects not only its initial conditions, but also the ongoing balance between expansion and gravitational attraction. Gravitational lensing offers a way to test this framework directly. When light from distant galaxies passes through a region of space, its path is bent by the mass it encounters. In dense clusters, the effect is strong, creating arcs and multiple images. In voids, the effect is subtler, but still measurable. Light passing through an underdense region is deflected less, leading to a slight reduction in magnification. By measuring these weak lensing signals, astronomers can map the distribution of dark matter, confirming that voids like Boötes are indeed underdense not only in galaxies but in total mass. This provides direct evidence that dark matter shapes the voids. The Boötes void, with its extreme size, also raises questions about the nature of dark matter itself. Standard cold, dark matter models can reproduce such voids, though they remain rare. If dark matter had different properties, if it were warm rather than cold, for example, or if it interacted with itself in unusual ways, the distribution of voids would change. Warm dark matter would smooth out small-scale fluctuations, reducing the contrast between filaments and voids. Self-interacting dark matter might alter the internal structure of halos. By comparing the observed voids to simulations with different types of dark matter, scientists can constrain which models are viable. The role of dark matter in shaping galaxy distribution also highlights the importance of initial conditions. The fluctuations from the early universe, imprinted in the cosmic microwave background, were random but statistically well defined. The amplitude of these fluctuations, combined with the amount and properties of dark matter, determined how quickly structures grew. The Butter's void is a product of these conditions, a place where the fluctuations happen to be lower than average, amplified over time by gravity. In this sense, the void is not just an accident but a natural consequence of the initial state of the universe combined with the behaviour of dark matter. Another aspect to consider is how voids interact with their surroundings. The boundaries of the Butter's void are defined by filaments and walls of galaxies, which themselves sit in dark matter over densities. The contrast between the void and its boundaries is created by the flow of matter. Dark matter streams out of the void, reinforcing the filaments. This interaction means that the void is not isolated but connected to the larger web. Its existence influences the distribution of galaxies around it, just as the distribution of galaxies around it defines its shape. The Butter's void also provides a test for dark energy, the mysterious component driving the accelerated expansion of the universe. Voids are particularly sensitive to dark energy because their expansion is less resisted by gravity than overdense regions. The rate at which voids grow depends on the balance between dark matter and dark energy. Measuring the Butter's void and others like it allows cosmologists to probe this balance. The dark matter framework sets the initial shape and distribution of voids, while dark energy modifies their growth. Together they define the large-scale structure. In everyday language, it can sound strange to describe emptiness as structured. But in physics, even voids are part of a framework. The Butter's void is not a mistake in the distribution of galaxies. It is a manifestation of the way dark matter sculpts space. Without dark matter, the universe would not have formed galaxies at all. With it, galaxies align along filaments, leaving voids behind. The Butter's void is an extreme example of this alignment, a place where the dark matter density was too low to form many halos, and so galaxies are rare. The study of dark matter in voids is ongoing. New surveys combining redshift measurements, lensing maps, and cosmic microwave background data continue to refine the picture. Each new dataset adds detail, confirming that the dark matter framework is consistent with what we see. Yet questions remain about the exact nature of dark matter, whether it is truly cold and collisionless, or whether more complex physics is involved. The Butter's void will remain part of these tests, a giant bubble in space that continues to challenge and confirm our models. To understand why the Butter's void exists at all, it is necessary to go back to the very beginning, to a time before galaxies, before stars, before atoms themselves, when the universe was less than a second old. The story of cosmic voids does not start billions of years after the Big Bang, when telescopes can map galaxies across vast distances. It starts in the first tiny fraction of a second, during an event known as cosmic inflation. Without inflation, the seeds that later grew into both filaments and voids could not be explained in a way that matches the patterns we observe today. Inflation is the idea that in the earliest instant of the universe, space itself expanded at an almost inconceivable rate. In less than a trillionth of a second, the universe grew from subatomic size to something macroscopic, far larger than the observable universe today extrapolated backward. This sudden expansion smoothed out the cosmos, making it nearly uniform everywhere, while at the same time amplifying tiny quantum fluctuations into macroscopic density variations. Those small fluctuations were the origin of everything we now see on cosmic scales. The evidence for this event comes primarily from the cosmic microwave background. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, light was released that has been travelling ever since. Today we detect that light as microwave radiation coming from every direction. Sensitive measurements of the microwave background show slight variations in temperature, about 1 part in 100,000. These variations correspond to tiny differences in density, and their statistical properties match what inflation predicts. They are nearly scale invariant, meaning that fluctuations occur with nearly the same strength across a wide range of sizes. They are also Gaussian, consistent with random quantum origins. Without inflation, it would be difficult to explain why regions of the universe that are now separated by billions of light years look so similar. There would not have been enough time for them to come into thermal equilibrium in the short age of the universe before recombination. Inflation solves this horizon problem by stretching a small, causally connected region into the entire observable universe. It also solves the flatness problem, explaining why the geometry of the universe is so close to flat. But for our purposes, inflation is most important because it created the initial fluctuations in density that later evolved into galaxies, clusters, filaments, and voids. Those fluctuations were minuscule, arising from the uncertainty of quantum fields. Normally, quantum fluctuations occur on scales far smaller than atoms, appearing and vanishing with no long-term consequence. During inflation, however, space expanded so quickly that these fluctuations were stretched across macroscopic distances. Once stretched, they became frozen into the fabric of space, imprinted as tiny variations in density. Later, when inflation ended and the universe settled into a slower expansion, these imprints remained as the starting conditions for structure formation. Regions that began slightly denser than average attracted more matter and grew into clusters. Regions that began slightly less dense became underdense and eventually grew into voids. The Bootes void, then, has its ultimate origin in these quantum fluctuations. Somewhere in the patch of space that became Bootes, the density was slightly lower than average, by perhaps a few parts in 100,000. Over billions of years, this tiny imbalance was amplified by gravity and cosmic expansion, until it became a vast bubble of emptiness, hundreds of millions of light years wide. The remarkable thing is that such an enormous structure can trace its roots to fluctuations that occurred on scales smaller than atoms, stretched by inflation to cosmic size. Simulations of the universe, which begin with the fluctuations observed in the microwave background, confirm this picture. When dark matter and normal matter are evolved under gravity from those initial conditions, the result is a web-like structure, with voids and filaments matching what surveys reveal. Inflation sets the initial spectrum of fluctuations, and the subsequent physics of dark matter and expansion shape them into the structures we see. The Bootes void is one extreme example, but it is part of this continuous chain from quantum physics to cosmic architecture. The role of inflation in shaping voids also connects to the statistics of large-scale structure. The distribution of void sizes, depths, and shapes depends on the properties of the initial fluctuations. If inflation had produced a different spectrum, say, with more power on small scales, or with strong non-Gaussian features, the resulting voids would look different. By measuring voids today, cosmologists can place constraints on inflationary models. The Bootes void, because of its rarity, is an important test case. While not every detail of one void can determine theory, the overall distribution of such extreme underdensities must be consistent with what inflation predicts. It is also important to recognize that inflation is not a single theory, but a family of models. Different versions predict slightly different features in the fluctuation spectrum. Some predict more variation at large scales, others predict small deviations from Gaussian statistics, others even allow for unusual topological features. Observing voids provides one way to test these possibilities. If the universe contained more large voids than expected, it might indicate an inflationary model that favoured stronger fluctuations at those scales. If voids showed unusual alignments, it might hint at exotic physics in the inflationary period. So far, observations are broadly consistent with the simplest models, but the Bootes void remains one of the extreme cases that keeps scientists cautious. Inflation also explains why voids are so round. The initial fluctuations were nearly isotropic, with no preferred direction. As a result, voids tend to be roughly spherical, even though they can be stretched by surrounding filaments. The Bootes void, when mapped, appears almost circular in cross-section, a signature of these early conditions. Without inflation, it would be harder to explain such symmetry. Another fascinating connection between inflation and voids involves the idea of cosmic variance. Because inflation generated fluctuations randomly, different regions of the universe can look slightly different. The Bootes void may simply be an unusually large fluctuation, a rare outcome of chance amplified over time. This randomness is expected, and it is part of why cosmologists speak in probabilities. The fact that Bootes exists does not contradict inflation, but rather demonstrates the range of possibilities inherent in the model. There is also speculation about whether very large voids might connect to even deeper aspects of inflation. Some theories of inflation suggest that it may have occurred not just once, but eternally, creating a multiverse of regions with different properties. In that view, our observable universe is just one bubble among many. Could the Bootes void be related to such a scenario? Most cosmologists think not. It can be explained by ordinary fluctuations, but the idea lingers in speculative discussions. Voids are, after all, among the largest coherent features we can observe, and they naturally invite questions about what lies beyond. The connection between inflation and voids is one of continuity across scales. At one end are quantum fluctuations smaller than atoms. At the other end are structures larger than hundreds of millions of light-years. Inflation bridges that gap, turning the smallest features of physics into the largest features of cosmology. The Bootes void, when seen this way, is not just a hole in the universe, but a fossil imprint of quantum events that took place in the first fraction of a second after the Big Bang. To measure and understand voids today is therefore to test not only dark matter and cosmic expansion, but also the physics of inflation. Each survey that maps galaxies, each analysis that quantifies voids traces back to those earliest instants. The Bootes void serves as an especially striking reminder of this connection. Its sheer size emphasizes how far the amplification has gone, from a fluctuation of 1 part in 100,000 to a region spanning 330 million light-years. When we speak about the Bootes void and why it is so large, we have to place it inside the broader context of the universe's expansion. The universe is not static. Space itself has been stretching ever since the Big Bang, and this stretching is the fundamental backdrop against which all galaxies, clusters, and voids evolve. To understand why Bootes looks the way it does today, and why galaxies inside it are so isolated, we have to walk carefully through what expansion means, how it was discovered, how it works in physics, and how it sculpts regions of emptiness into vast, nearly spherical cavities of space. The discovery of expansion began in the early 20th century, when Vesto Slipher first noticed that most galaxies had their spectral lines shifted toward the red. Later, Edwin Hubble quantified the relationship between distance and velocity. Galaxies farther away were moving away faster, and the rate of this relationship became known as the Hubble constant. What Hubble and his contemporaries realized was that galaxies were not flying through space like shrapnel from an explosion. Instead, the fabric of space itself was stretching, carrying galaxies along with it. This is why more distant galaxies recede faster. The more space there is between us and them, the more stretching occurs. This insight transformed cosmology. If the universe is expanding, then in the past it must have been smaller and denser. Extrapolating backward leads to the Big Bang, a state where all of space and matter were compressed into an extremely hot and dense condition. Since that beginning, space has expanded, cooling and thinning. Structures like galaxies and clusters formed as matter clumped under gravity, but the expansion never stopped. It has continued, shaping the large-scale arrangement of matter and emptiness alike. For voids such as booties, expansion is critical. In overdense regions, gravity works against expansion. Galaxies and clusters may not participate fully in the Hubble flow because their mutual gravity holds them together. Inside voids, the opposite happens. With less matter present, gravity is weaker, and the expansion proceeds more freely. In fact, galaxies near the edges of voids can be pulled outward, making the void grow even larger. Over billions of years, this effect magnifies the original underdensity, turning small gaps into enormous cavities. The Boots void exists as it does today because the expansion of space has enhanced its emptiness. One way to picture this is to imagine raisins baked into rising dough. As the dough expands, the raisins move apart. In regions where there are fewer raisins to begin with, the gaps grow faster. The Booter's void is like a part of the loaf where the raisins were especially sparse, and as the dough rose, that region became an oversized pocket of bread with very few raisins inside. This analogy, simple as it is, captures the essence of how cosmic expansion interacts with density differences to sculpt the web of filaments and voids. Physicists describe the expansion of the universe using general relativity. The key equation is the Friedmann equation, which relates the expansion rate to the density of matter, radiation, curvature, and dark energy. In the early universe, radiation dominated, then matter, and today dark energy dominates. Each of these eras influenced how quickly expansion occurred. During the matter-dominated era, gravity slowed the expansion, allowing structures like galaxies and voids to form. As dark energy became dominant a few billion years ago, expansion accelerated, stretching voids even more quickly. The Booter's void has therefore grown not only because of its initial underdensity, but also because of the accelerated expansion of space itself. Measurements of expansion today come from multiple methods. The Hubble constant is determined from nearby galaxies, while the cosmic microwave background provides constraints from the early universe. Supernova observations have shown that the expansion is accelerating, revealing the presence of dark energy. Baryon acoustic oscillations, subtle patterns in the distribution of galaxies, act as standard rulers to measure distances and confirm the expansion history. All of these methods build a consistent picture. The universe is expanding, the rate is changing over time, and this expansion drives the growth of voids. The Booter's void provides a natural laboratory to study this. By mapping the galaxies near its edges, astronomers can see how they are moving relative to the Hubble flow. If they are streaming outward, it confirms that the void is expanding faster than the denser regions. This has indeed been observed in voids generally. Galaxies at the boundaries tend to move away from the centres. In booties, given its size, this effect is pronounced. It helps explain why the void is not just empty but so large. The ongoing expansion has amplified its emptiness for billions of years. Another way expansion influences voids is through their shapes. In simulations, voids tend to become more spherical over time. Initially, density fluctuations can be irregular, stretched in one direction or another, but as the universe expands, the differences smooth out and voids around themselves. The Bootis void, with its roughly spherical form, is an example of this. Its geometry is not an accident, but a result of how expansion distributes matter evenly across underdense regions. Expansion also determines how galaxies inside voids evolve. With fewer neighbours, interactions are rare. The isolation allows these galaxies to retain their gas longer, fueling star formation at a slow but steady pace. The ongoing expansion separates them even further, ensuring their solitude persists. If the universe were not expanding as it is, void galaxies might have different properties. Their current state is a direct outcome of the expansion stretching space around them. The influence of expansion extends beyond individual voids. It defines the cosmic web itself. As space stretches, filaments thin and lengthen, clusters grow farther apart, and voids enlarge. On the larger scales, the distribution of galaxies becomes more uniform, matching the cosmological principle. The Bhuta's void, sitting at hundreds of millions of light-years across, reflects the interplay between local underdensity and global expansion. It is not merely a static whole, but a dynamic feature sculpted continuously by the stretching of space. There is also the future to consider. As expansion accelerates under the influence of dark energy, voids will continue to grow. In trillions of years, if dark energy behaves as we think, galaxies will recede beyond each other's horizons, and voids will dominate the visible universe. Structures like the Bhuta's void are a glimpse of that future, when emptiness becomes the defining characteristic of the cosmos. The Bhuta's void is not only a present-day feature, but a preview of the universe's long-term trajectory. To fully appreciate the effect of expansion on Bhuta's, one can think in terms of time. If we could watch the void over billions of years, we would see galaxies streaming outward, the walls thickening, the centre becoming emptier. The process is gradual but relentless. The same laws that expand the entire universe also hollow out these enormous regions. Each galaxy measured, each redshift recorded confirms that this is not just theoretical. It is happening now, and the Bhuta's void is one of the most dramatic examples. In cosmology, expansion is not an optional detail. It is the foundation of the entire model. Without it, voids would not grow, clusters would not form, and the large-scale structure would look entirely different. The Bhuta's void embodies this reality. Its size and shape are the outcome of billions of years of expansion, acting on an initial underdensity seeded during inflation. Its present form is a balance of dark matter, pulling matter into filaments, and dark energy stretching space outward. Measuring and understanding it is therefore a way of measuring and understanding expansion itself. When cosmologists first realized that the universe was expanding at an accelerating rate, it forced a major shift in how we think about the large-scale structure of space. Until the late 20th century, most expected that the expansion would gradually slow, pulled back by the combined gravity of all the matter in the universe. Instead, observations of distant supernovae revealed the opposite. Galaxies are not just moving away, they are moving away faster and faster over time. The agent responsible for this is what we now call dark energy, a form of energy that permeates all of space and drives acceleration. While its nature remains mysterious, voids like Bhuta's provide a natural stage to see its effects in action. The reason voids are especially sensitive to dark energy is that they are places where matter is already scarce. In clusters and filaments, the pull of gravity competes strongly with cosmic expansion. Galaxies are bound to one another, and their local dynamics can mask the influence of dark energy. In voids, there is little matter to resist expansion. The stretching of space acts more freely, making voids expand faster than the universe as a whole. This makes them amplifiers of dark energy's influence. Measuring how quickly voids grow can tell us how strong dark energy is and how it behaves over time. In the Bhuta's void, the effect of dark energy has been at work for billions of years. The void began as a slightly underdense region seeded during inflation, grew during the matter-dominated era as mass flowed outward, and in the last few billion years, its expansion has been further accelerated by dark energy. This acceleration enhances the contrast between the void and the surrounding filaments. The walls become denser as more matter accumulates, while the interior becomes emptier as expansion outpaces any tendency for matter to flow back in. The result is the sharp definition of the Bhuta's void as one of the largest cavities in the cosmic web. The role of voids in testing dark energy has become an important area of research. Observations show that galaxies near the boundaries of voids are moving outward relative to the centre, consistent with the idea that voids expand. By comparing these velocities to predictions, scientists can constrain cosmological parameters. If voids expand more quickly than expected, it may indicate stronger dark energy or a different form of it. If they expand more slowly, it could suggest modifications to gravity itself. Either way, voids provide a test that complements other methods, such as studying supernovae or the cosmic microwave background. One particularly important observational effect involving voids is the integrated Sachs-Wolf effect. This is a subtle change in the energy of photons from the cosmic microwave background as they pass through large structures. In overdense regions, photons gain and lose energy symmetrically, leaving no net effect. In underdense regions, however, the accelerating expansion means that photons lose slightly more energy than they gain, leaving a small cold spot in the microwave background. Measuring this effect requires stacking many voids, but detections have been reported. The Bootes void, given its size, should contribute strongly to this signal, and studying it can help confirm the imprint of dark energy on the oldest light in the universe. Another way voids help probe dark energy is through their shape and alignment. In an accelerating universe, voids become more spherical as expansion smooths out anisotropies. By measuring the shapes of many voids in galaxy surveys, astronomers can compare them to simulations with different cosmological parameters. Deviations from sphericity can signal differences in dark energy's behaviour. The Bootes void, being unusually spherical already, fits the pattern predicted by an accelerating universe. Dark energy is often modelled as a cosmological constant, a uniform energy density that does not change over time. But other models are possible. Some suggest that dark energy could vary, either in strength or in equation of state, which is the ratio of its pressure to its density. Voids are especially useful for testing these alternatives. If dark energy evolves, the growth rate of voids will deviate from predictions. The Bootes void, as an extreme case, becomes one of the best places to look for such deviations. Its sheer size makes small changes in expansion more noticeable. The link between voids and dark energy also highlights the importance of precision surveys. Mapping galaxies with high accuracy allows scientists to identify voids, measure their sizes, and track their growth. The Sloan Digital Sky Survey has already provided a wealth of data, but upcoming projects like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are expected to push this much further. These surveys will map tens of millions of galaxies, allowing for detailed void catalogues. Bootes will remain a standout feature in these catalogues, a reference point for testing models of dark energy. From a theoretical standpoint, voids also offer a way to test modifications to general relativity. Some alternative theories of gravity attempt to explain cosmic acceleration without invoking dark energy. These models often predict different behaviours for voids, such as faster or slower expansion, or different velocity profiles for galaxies near their edges. Comparing the observed properties of voids to these predictions can rule out or support such theories. The Bootes void, with its extreme emptiness, magnifies these effects and makes them easier to detect. It is striking to realise that one of the largest known structures of emptiness is also one of the best laboratories for probing the deepest mystery in cosmology. Dark energy cannot be seen directly, but its fingerprints are written in the way voids expand. The Bootes void, because of its scale, acts as a magnifying lens for these fingerprints. Each galaxy drifting outward along its boundaries, each photon slightly cooled as it passes through, is part of the evidence for a force that shapes the fate of the cosmos. The connection between voids and dark energy also raises questions about the future. If dark energy continues to act as it does now, voids will grow larger and larger, eventually dominating the universe. The cosmic web will thin out, clusters will recede beyond one another's horizons, and isolated galaxies will find themselves adrift in vast oceans of nothing. The Buddhist void is a preview of this future, a place where emptiness has already taken over on scales of hundreds of millions of light years. In trillions of years, such voids may be the norm, with filaments and clusters reduced to islands surrounded by unending darkness. From a human perspective, it is remarkable to think that by studying emptiness, we are learning about the ultimate destiny of the universe. Dark energy may remain mysterious in its essence, but its effects are measurable, and voids like boats are among the clearest expressions of those effects. They show how space itself evolves, not just matter within it. They reveal how the balance between gravity and expansion has tipped, and how the universe has entered a new phase where emptiness grows faster than structure. The Buddhist void, then, is not just a curiosity. It is a key to understanding the force that governs the larger scales. Its growth reflects the influence of dark energy, its shape reflects the smoothing power of accelerated expansion, and its emptiness amplifies the contrast that makes dark energy's effect measurable. The void is both a physical structure and a scientific tool, linking observations of galaxies to the most fundamental questions of cosmology. When people first hear about voids in the universe, it can sound as if they are places where gravity simply does not matter, as though the lack of matter meant a lack of influence altogether. But in cosmology, even emptiness plays a role in shaping motion. Gravity is not only about what is present, but also about what is absent. A void like the Buddhist void exerts a subtle but measurable effect on the galaxies around it, pulling and pushing them in ways that reveal how underdense regions shape the cosmic web. To understand this, we need to step into the physics of how gravity works when matter is unevenly distributed, and how absence can generate as much influence as presence. The first key point is that voids are defined relative to the average density of the universe. Imagine that space were filled evenly with matter everywhere. In that case, the gravitational pull on any one point would cancel out in all directions, leaving no net force. But if one region is less dense than average, it changes the balance. Galaxies around the void feel slightly less pull from the interior because there is less mass inside and relatively more pull from the denser filaments surrounding it. The result is that galaxies near the boundaries of a void tend to move outward, away from the centre, as if the void itself were repelling them. This is not repulsion in the ordinary sense. Gravity does not push, it only pulls. But the imbalance of pulls means that galaxies drift away from the emptiness toward denser regions. In cosmology, this effect is described as the peculiar velocity field associated with voids. Peculiar velocities are motions on top of the Hubble expansion. The universe's general expansion carries galaxies apart, but peculiar velocities add local variations. In voids, these peculiar velocities are directed outward, enhancing the growth of the cavity. In dense clusters, peculiar velocities are directed inward, pulling galaxies together. The Buddhist void represents an extreme case of this outward flow, with galaxies near its edges slowly but steadily streaming away from its centre. This outward flow has been measured in surveys. By comparing galaxy redshifts to their expected positions in the Hubble expansion, astronomers can detect deviations that signal peculiar velocities. In voids, these deviations show galaxies moving faster than average away from the centre. The Buddhist void's immense size means that the effect extends across hundreds of millions of light years, influencing not just individual galaxies but entire groups and clusters along its walls. It acts as a vast gravitational basin flipped inside out, not gathering matter but allowing it to leak away. One way to picture this is to think of a valley and a hill in a landscape. Matter flows into valleys and away from hills. In the universe, over dense regions are valleys, pulling matter in, while under dense regions are hills, allowing matter to roll away. The Buddhist void is one of the biggest hills, stretching across a significant fraction of the cosmic web, pushing galaxies outward towards surrounding filaments. This gravitational analogy helps explain why voids are not static. They evolve dynamically, growing larger as matter evacuates them. The influence of voids extends beyond local motions. They also affect how light travels. Gravitational lensing, which is the bending of light by mass, works differently in underdense regions. In clusters, light is bent inward, magnifying and distorting background galaxies. In voids, the opposite occurs. Light is bent outward, slightly demagnifying the background. This weak lensing effect has been measured statistically by stacking many voids. It shows that voids are indeed underdense in total mass, including dark matter. The Boots void, due to its size, should produce a measurable signal, confirming that emptiness has a gravitational fingerprint just as real as presence. Another effect, as mentioned earlier, is the integrated Sachs-Wolf effect, where photons from the cosmic microwave background lose energy when passing through expanding voids. This is a direct gravitational interaction. The potential well of a void changes as photons traverse it, leaving a small but detectable cold spot in the microwave background. These cold spots align with the locations of known voids, confirming their influence. The Bootes void, if analysed in this way, would be expected to leave one of the strongest signals, though the challenge is that the effect is subtle and requires stacking data from many regions to reduce noise. The gravitational influence of voids also plays into how we measure the growth of structure. By observing how fast galaxies move relative to voids, scientists can test cosmological parameters. If voids expand faster than predicted, it might suggest stronger dark energy or weaker gravity. If they expand more slowly, it could imply different physics altogether. This is why voids are increasingly used in precision cosmology, alongside clusters and supernovae. Their peculiar velocity fields, lensing signals, and microwave background imprints all serve as probes of fundamental physics. For the Bootes void specifically, its size makes it an extreme case for these effects. The gravitational pull of its emptiness stretches across hundreds of millions of light years. Galaxies that might otherwise have clustered more densely have been drawn outward, reinforcing the surrounding walls. This is why voids are not isolated pockets, but integral parts of the cosmic web. The outflow from voids feeds the inflow to filaments. The two processes are linked, creating the sponge-like pattern observed in redshift surveys. It is worth noting that the idea of emptiness shaping motion is not entirely new. Even in Newtonian gravity, if you remove mass from a region, the surrounding matter shifts in response. General relativity provides a deeper framework, describing voids as regions where the metric of space itself evolves differently. The absence of matter changes the curvature of space-time, which in turn alters the paths of both galaxies and photons. This connection between absence and curvature is what makes voids powerful laboratories for testing gravity itself. There are also subtler gravitational effects. Voids influence not just motions, but also the growth rate of small-scale structures inside them. Because the density is low, galaxies inside voids experience weaker tidal forces. This allows them to evolve differently, often retaining their disks and forming stars longer than galaxies in dense clusters. In a sense, the gravitational calm of a void is as important as the outward flow. It creates an environment where galaxies are less disturbed, and their evolution carries the imprint of this gravitational quiet. The Bootes void, being so large, magnifies all of these gravitational phenomena. Its outflow is stronger, its lensing effect more extended, its imprint on background radiation more significant, and its internal calm more pronounced. Studying it allows astronomers to test theories at an extreme. If gravity behaved differently than expected, a void of this size would reveal it. The fact that Bootes can be explained by standard gravity and dark energy models strengthens confidence in them, but it also leaves room for continued testing. From a practical perspective, mapping the gravitational effects of voids requires precision. Redshift surveys provide the galaxy distributions, but peculiar velocities require deeper analysis. Weak lensing requires statistical stacking of thousands of background galaxies. Sachs-Wolf imprints require sensitive maps of the microwave background. Each of these methods has confirmed the gravitational influence of voids, building a consistent picture. The Butter's void, though harder to study in detail because of its distance and size, fits within this framework. The gravitational role of voids also extends into predictions for the future of the universe. As expansion accelerates, voids will dominate more and more of the volume. Galaxies will be drawn outward faster, filaments will thin, and the cosmic web will gradually dissolve. The Butter's void is a preview of this process, a place where the gravitational effects of emptiness already define the landscape. It shows what the universe may look like on even larger scales in the distant future, when emptiness is the norm rather than the exception. By appreciating the gravitational effects of voids, we can see that emptiness is not passive. It is an active participant in cosmic evolution. The Butter's void, far from being just a hole, is a gravitational engine of sorts, shaping motions, bending light, and influencing structure growth. Its very lack of matter defines the flows of matter elsewhere. This is the paradox of voids. Absence creates presence, emptiness shapes fullness. When astronomers first began to map the Butter's void, the most striking feature was its absence of galaxies. Yet the closer they looked, the more they realized that it is not entirely empty. A few dozen galaxies are scattered across its 330 million light-year span, faint specks of light adrift in an ocean of darkness. Compared to the thousands that should exist if the void had average density, these galaxies are rare outliers. But their very presence is valuable, because they reveal how isolation changes the story of galaxy evolution. To understand Butter's, it is not enough to describe its emptiness. We must also examine the lives of the few galaxies that endure within it. These galaxies are sometimes called void galaxies, and they differ in important ways from their counterparts in denser regions. In clusters, galaxies are constantly influenced by their neighbours. They collide, merge, strip gas from one another, and are subjected to the gravitational tides of hundreds of surrounding systems. In filaments, galaxies interact less violently, but still feel the pull of their network. Inside Butter's, the story is different. A galaxy there might have no close neighbour for tens of millions of light-years. This solitude shields it from the disruptive interactions that shape cluster galaxies. As a result, void galaxies often retain their gas longer, continue forming stars later into cosmic history, and show bluer colours, which are signs of younger stellar populations. The rarity of these galaxies makes them difficult to study in detail. Many are faint dwarfs, their light barely visible even to modern telescopes. But when astronomers do capture their spectra and images, patterns emerge. One is that void galaxies are disproportionately late-type spirals with loosely wound arms and ongoing star formation. This is consistent with the idea that without environmental stress, galaxies evolve more gently, keeping their disks intact. Elliptical galaxies, by contrast, form more often in clusters, where frequent mergers disrupt spirals and build spheroidal shapes. The Butter's void contains very few ellipticals, which fits the expectation that galaxy morphology depends strongly on environment. Another difference is in gas content. In clusters, galaxies often lose their cold gas through processes like ram pressure stripping, where hot cluster gas pushes it out, or tidal stripping, where neighbours pull it away. In voids, such processes are rare. Observations suggest that void galaxies can hold onto their hydrogen gas for longer, giving them a steady supply of material for star formation. This prolongs their star-forming lifetimes compared to similar galaxies in crowded regions. Some void galaxies even appear unusually gas-rich, with extended reservoirs that may allow them to form stars far into the future. The star formation rates of void galaxies also reflect this. Many show active formation of young blue stars despite being in regions where cosmic time has aged most galaxies. This suggests that voids act as protective environments, slowing down the processes that shut down star formation elsewhere. In clusters, galaxies can become quiescent as interactions exhaust their gas. In Butter's, galaxies continue to live younger lives, their isolation-preserving conditions that elsewhere fade. Studying these galaxies also helps cosmologists understand how halos of dark matter function in underdense regions. Every galaxy sits in a dark matter halo, and the formation of halos depends on environment. In voids, halos are less massive and less numerous. The galaxies inside Bootis therefore tend to be smaller, reflecting the low-mass halos that could form in such an underdense setting. These low-mass halos provide fewer opportunities for mergers, which is why void galaxies are more likely to remain small spirals or dwarfs. Their very survival shows how dark matter distribution controls galaxy properties. There are exceptions, of course. A few larger galaxies have been found inside voids, and their existence raises interesting questions. Did they form in place, or were they drawn in from denser regions? Simulations suggest that most void galaxies form in situ, from the rare density peaks that exist even in underdense regions. But some may drift inward along thin filaments that penetrate the void. These faint filaments, sometimes called tendrils, connect void galaxies to the larger web, albeit tenuously. The Boots void likely contains such substructures, invisible in early surveys but hinted at in modern maps. These delicate filaments may act as lifelines, feeding gas and matter to galaxies within the void. One of the most fascinating aspects of void galaxies is their potential to test models of galaxy formation. Because they evolve in relative isolation, their properties reflect more closely the intrinsic processes of star formation and feedback, without the complications of environmental effects. By comparing void galaxies to cluster galaxies, astronomers can disentangle which features are due to internal physics and which are due to environment. For example, if both void and cluster spirals show similar relations between mass and star formation rate, it suggests that internal processes dominate. If they differ, it reveals how environment shapes outcomes. The Bootis void, with its extreme isolation, provides a natural control sample. There is also the question of how galaxies inside voids will evolve in the future. As cosmic expansion accelerates, their isolation will only increase. Already far from neighbours, they will become even more alone as surrounding filaments stretch away. Over trillions of years, they may become stranded, cut off from external sources of gas, living only on their internal reserves. Their eventual fates will depend on how efficiently they recycle gas through stellar winds and supernovae. In this way, the Bootis void is a preview of the universe's long-term isolation, where all galaxies may eventually find themselves alone in expanding emptiness. For astronomers, the study of void galaxies is challenging but rewarding. Their faintness requires deep surveys and sensitive instruments. Radio telescopes are particularly useful, since they can detect the hydrogen gas that fuels star formation. Observations in the 21 centimeter line of neutral hydrogen reveal extended reservoirs around void galaxies, confirming their gas-rich nature. Optical telescopes, meanwhile, show their morphology and stellar populations. Combining these data builds a fuller picture of how life in a void differs from life in a filament. The Bootis void has inspired targeted searches for such galaxies. While early surveys identified only a few, newer instruments have revealed more. Each discovery adds a piece to the puzzle. These galaxies are not just curiosities, they're keys to understanding how environment shapes cosmic evolution. In some ways, they are relics of earlier cosmic times, living more slowly than their crowded counterparts. Their blue colours and spiral arms are reminders that star formation is still active, even in one of the most desolate regions of the universe. The gravitational calm of the void also allows astronomers to study galaxy dynamics in cleaner conditions. In clusters, measuring rotation curves is complicated by interactions and disturbances. In voids, galaxies rotate in relative isolation, making them good laboratories for testing dark matter distribution within halos. By studying how stars and gas move in these galaxies, scientists can refine models of how dark matter behaves on small scales. The Bootis void thus serves as a laboratory not only for cosmology, but also for galactic astrophysics. It is striking that the largest hole in the universe still contains enough to keep astronomers busy. The few galaxies scattered inside it carry disproportionate scientific value. They are the survivors of a cosmic lottery, the rare systems that manage to form in a region of scarcity. Each one represents a triumph of structure over emptiness, of star formation over isolation. Their properties, preserved by solitude, provide insights that galaxies and clusters can no longer offer. From a broader view, these galaxies also connect the scales of physics. The Bhuta's void, hundreds of millions of light-years across, is defined by the distribution of dark matter and cosmic expansion. The galaxies inside it, only tens of thousands of light-years wide, are shaped by the physics of gas cooling, star formation and feedback. Studying them links the largest scales to the smallest, showing how the universe is connected across orders of magnitude. As surveys become more powerful, the Bhuta's void will continue to be mapped in greater detail. More galaxies may be discovered inside it, perhaps faint dwarfs too dim to have been seen before. Each one will add to our understanding of what it means to live in cosmic solitude. The Bhuta's void is not empty after all. It is a stage where a few galaxies live out quiet, extended lives, offering a glimpse of what the universe might one day become as expansion carries everything farther apart. The Bhuta's void may be the most famous example, but it is not the only one. Other large voids exist, each with their own characteristics and their own populations of isolated galaxies. By comparing them, astronomers can see whether Bhuta's is truly unique or simply one extreme example of a universal phenomenon. The discovery of the cosmic microwave background changed cosmology forever, because it gave scientists a way to look back nearly to the beginning of time. It is the oldest light we can see, released when the universe was about 380,000 years old, long before stars or galaxies existed. For most of its journey across nearly 14 billion years, this light has travelled almost undisturbed, carrying with it a record of conditions in the early universe. But as it passes through large-scale structures on its way to us, it is altered in subtle ways. This makes the microwave background not just a snapshot of the past, but also a canvas that records the influence of voids, clusters, and filaments it encounters. To understand the Bhuta's void in full context, it helps to see how voids interact with this ancient radiation, and what those interactions reveal about the physics of the universe. The cosmic microwave background, often abbreviated as the CMB, is nearly uniform. Its temperature is about 2.7 Kelvin, only a few degrees above absolute zero. Across the sky, it varies by only a few parts in 100,000. These small variations, or anisotropies, reflect tiny density differences in the early universe, the seeds from which all later structure grew. Inflation stretched quantum fluctuations into these density variations, which later evolved into galaxies, clusters, and voids. The pattern of anisotropies matches predictions from inflation remarkably well, but the microwave background also carries secondary imprints, changes that occurred after it was released. These include effects from reionization, gravitational lensing, and most relevant here, the Sachs-Wolf effect. The Sachs-Wolf effect, first described in the 1960s, occurs when photons travel through gravitational potential wells. In simple terms, light loses energy when climbing out of a gravitational well and gains energy when falling in. If the potential is static, the gains and losses cancel, leaving no net change. But if the potential evolves while the photon is inside it, there can be a leftover effect. This is where voids and dark energy come in. In an expanding universe dominated by dark energy, gravitational potentials do not remain constant. Voids, being under dense regions, evolve over time, expanding faster than the universe as a whole. Photons that pass through them experience a slight net loss of energy, appearing a little colder when they reach us. This particular version of the effect is called the integrated Sachs-Wolf effect. It is incredibly subtle, on the order of microkelvins, far smaller than the primary anisotropies from the early universe. Detecting it requires careful statistical methods, usually by stacking the microwave background signal across the positions of many voids. Still, evidence has been found that supports its existence, and this strengthens our confidence that voids expand and that dark energy influences them. The Boots void, by virtue of its size, should produce one of the strongest individual integrated Sachs-Wolf signals. Its vast expanse, 330 million light-years across, means that photons spend a significant amount of time crossing it. During that time, the underdense region evolves, and the photons emerge slightly cooler. Detecting this specific signal is difficult because it is buried under the noise of larger-scale fluctuations, but in principle, the Bootes void represents one of the clearest natural laboratories for observing the effect. Another way the microwave background interacts with voids is through gravitational lensing. While clusters magnify and distort the background strongly, voids produce the opposite, a slight demagnification, because there is less mass to bend the light inward. This weak lensing effect leaves a subtle signature in the statistical properties of the CMB. When analysed in detail, the background shows that light paths have been smoothed by underdense regions. Bootes, being so large, contributes to this smoothing, demonstrating that even emptiness bends light, though outward rather than inward. The connection between the CMB and voids also highlights how different epochs of cosmic history are linked. The anisotropies we see in the microwave background come from the very beginning, imprinted when the universe was young. The integrated Sachs-Wolf effect adds information from much later times, when dark energy began to dominate a few billion years ago. By comparing the two, cosmologists can test how the universe has evolved across its entire history. Voids like Bootes are central to this comparison, bridging the early seeds to the present-day structure. In practical terms, measuring the imprint of voids on the CMB requires combining galaxy surveys with microwave background maps. Surveys identify the positions and sizes of voids, while satellites like WMAP and Planck provide the background data. By correlating the two, scientists look for consistent signals. Positive correlations mean that voids indeed leave an imprint. This method has been applied to many voids, producing detections that match theoretical expectations. Bootes, while difficult to isolate, fits into this framework, reinforcing its role as part of the cosmic laboratory. One of the challenges in interpreting the CMB void connection is cosmic variance. The primary anisotropies are random, and on large scales they dominate the signal. Distinguishing the small imprint of voids from this background noise is difficult. Statistically, however, the combined signal of many voids rises above the noise. Bootes is one of the largest contributors to that combined signal, but detecting its individual effect remains a challenge. Future high-resolution observations may improve this, making it possible to identify the fingerprints of individual giant voids. The study of the microwave background and voids also has implications for testing alternatives to dark energy. Some theories suggest that the apparent acceleration of the universe could be explained by large-scale inhomogeneities rather than a uniform dark energy field. In such models, voids play a central role because they could mimic the observational signatures of acceleration. The integrated Sachs-Wolf effect becomes a critical test. If voids do not leave the expected imprint, it could suggest that acceleration arises from geometry rather than energy. So far, the evidence supports dark energy, but voids like Bootes remain crucial in keeping this question open. Another subtle effect comes from rhionization, the period when the first stars and galaxies rhionize the intergalactic medium. This process scattered some of the microwave background photons, adding secondary anisotropies. Voids, with their lower galaxy density, contribute less to rhionization. This means that the microwave background passing through voids carries a cleaner signal, less contaminated by scattering. Bootes, being so underpopulated, is effectively a window through which the CMB can pass, with fewer interruptions preserving its information. The link between voids and the microwave background is not only about what we can measure today, but also about what it tells us regarding the origin of voids themselves. The anisotropies in the CMB show the seeds of underdense regions directly. When we see a cold spot in the background map, it corresponds to a region that was less dense in the early universe. Over time, that region evolved into a void. The Bootes void can thus be traced back to a faint patch in the microwave background, a direct line from the earliest light to the present-day structure. This continuity makes the CMB one of the most powerful tools for studying voids. It is remarkable to think that a photon released nearly 14 billion years ago could tell us something about a hole hundreds of millions of light years wide. Yet this is the power of cosmology. By connecting the microwave background to the present structure, we can see the universe not as static snapshots, but as an evolving story. The Bootes void is one of the characters in that story, and the CMB is the ancient record that describes its beginnings. As observations improve, the connection between voids and the microwave background will become even more important. Future missions with higher sensitivity and resolution may be able to detect the integrated Sachs-Wolf effect from individual giant voids like Bootes. Such measurements would directly confirm the influence of dark energy on large-scale structures. They would also help refine models of inflation, since the initial conditions imprinted in the CMB determine how voids form. In this way, the study of the microwave background and voids closes the loop from the earliest universe to the structures we see today. When astronomers confront something as vast as the Bootes void, the natural next step is to ask whether our theoretical models of the universe can explain it. Observations are the foundation, but without a framework to interpret them, they remain isolated facts. The Bootes void is not simply a curiosity on the map of galaxies. It is a test of whether the physics we use to describe the cosmos is complete. Theoretical models must account for how such an enormous underdensity can arise, how common or rare it should be, and what its properties imply about matter, gravity, and cosmic history. The starting point is the Standard Model of Cosmology, often referred to as LCDM. This shorthand stands for lambda, the cosmological constant associated with dark energy and cold dark matter, the form of matter that dominates gravitational dynamics. Together with ordinary baryonic matter and radiation, these components define the evolution of the universe. LCDM has become the prevailing framework because it successfully explains a wide range of observations, from the anisotropies in the cosmic microwave background to the large-scale clustering of galaxies. The question is whether Bootes and other giant voids fit naturally into this model or strain its predictions. In LCDM, structures grow from tiny density fluctuations seeded during inflation. These fluctuations are described statistically with a nearly scale-invariant spectrum. Some regions begin slightly denser, others slightly less dense. Gravity amplifies the differences, pulling matter into overdense regions and evacuating underdense ones. Over billions of years, this produces the cosmic web, with its filaments, clusters, and voids. In simulations based on LCDM, voids appear naturally. Their sizes and distributions depend on the details of the initial fluctuations and the balance of dark matter and dark energy. Most voids are tens of megaparsecs across, but occasionally rare large ones emerge. The Bootes void, at over 100 megaparsecs in radius, sits at the extreme tail of this distribution. This means that Bootes is not impossible under LCDM, but it is rare. Theoretical models predict that voids of its size should exist in small numbers across the observable universe. That is consistent with what surveys show. Bootes is not unique, but it is among the largest. Its presence therefore strengthens confidence in LCDM, because the model allows for such extremes. At the same time, it motivates scientists to refine their predictions, ensuring that simulations reproduce not only the average distribution of voids, but also the outliers. The process of modelling voids involves both analytic theory and numerical simulation. Analytic approaches treat voids as underdense perturbations that expand over time. Similar to how overdense regions collapse into clusters, the mathematics can be framed in terms of the spherical expansion model, which describes how an underdensity evolves in an expanding universe. These models show that voids should become emptier and more spherical over time, matching what is observed. They also predict relationships between void size, density contrast, and redshift, which can be tested against surveys. Numerical simulations go further by including the full complexity of dark matter, baryonic physics, and cosmic expansion. By evolving billions of particles under gravity, simulations create a three-dimensional web that can be compared directly to surveys. In these simulations, voids form as part of the natural structure. Boot-sized voids appear occasionally, though rarely, confirming that they are consistent with the model. These simulations also reveal substructure within voids, thin tendrils of galaxies and small groups that align with faint dark matter filaments. This matches the observations of isolated galaxies inside boots, suggesting that even the emptiest regions are not entirely barren. Alternative models have also been proposed, particularly in the years when Bootes was first discovered. Some speculated that such a large void might point to physics beyond LCDM, such as modified gravity, warm dark matter, or exotic forms of dark energy. Each of these models predicts different patterns of structure formation. Warm dark matter, for example, would smooth out small-scale fluctuations, leading to fewer small galaxies in voids. Modified gravity could change how quickly underdensities expand. Exotic dark energy could alter the growth rate of large structures. By comparing the properties of voids to these predictions, cosmologists can rule out or constrain alternatives. So far, LCDM remains the best fit, but the existence of boots ensures that these questions continue to be asked. One intriguing theoretical possibility is that voids themselves might play a role in the observed acceleration of the universe. Some models propose that if the universe were inhomogeneous on very large scales, the cumulative effect of voids could mimic cosmic acceleration without the need for dark energy. In such models, boots and other supervoids are not just structures within the universe, but contributors to its overall dynamics. However, detailed calculations and observations have shown that this explanation cannot fully account for the data. Dark energy remains necessary, but voids still provide valuable checks on whether our assumptions about homogeneity hold true. Theoretical models also attempt to describe the statistics of voids in detail. Just as the distribution of galaxies can be characterized by correlation functions and power spectra, voids can be described by their size distribution, shapes, and density profiles. These statistics depend sensitively on cosmological parameters, making voids useful for constraining them. For example, the abundance of large voids is influenced by the amplitude of the initial fluctuations, known as S8, and the fraction of matter in dark energy. The Bootes void, as one of the largest examples, is especially sensitive to these parameters. If too many Bootes-like voids existed, it would imply different values than what other observations suggest. The fact that Bootes fits into the expected rarity strengthens the consistency of the model. Another aspect of modelling voids involves their dynamics. Voids are not static bubbles, but evolving regions with matter flowing outward. Theoretical models predict velocity fields around voids, which can be compared to observations of galaxy motions. These velocity fields also test gravity itself. General relativity makes specific predictions for how voids expand. Alternative theories, such as scalar tensor models or FR gravity, predict different velocity profiles. By studying Bootes and similar voids, cosmologists can test these predictions directly. So far, general relativity has passed these tests, but the precision of future measurements may uncover new insights. Theoretical interest in voids has grown in recent years because they provide complementary tests to traditional cosmological probes. Clusters of galaxies test high-density environments, while voids test low-density ones. Together they bracket the range of conditions in the universe. The Bootes void, being extreme, sits at the boundary of these tests. It challenges models to reproduce not just average conditions, but the rarest extremes. This is essential because a complete theory must explain both the common and the exceptional. One of the remarkable things about theoretical models of voids is how they connect physics across scales. Inflation sets the initial conditions at subatomic scales. Dark matter and gravity shape those conditions into cosmic structures. Dark energy modifies their growth over billions of years. The Buddha's void embodies this entire chain. It began as a quantum fluctuation, evolved under dark matter dynamics, and was stretched by dark energy into its current form. Modelling it requires integrating physics from the earliest universe to the present. From the perspective of simulations, Boots also demonstrates the importance of statistical extremes. In any distribution, rare events occur, and the Boots void is one such event. Simulations show that while most voids are small, a few giant ones will exist. This statistical reality ensures that Booties is not an anomaly but part of the natural spectrum. Theoretical models must account for these tails as well as the averages. This is why cosmologists run simulations with billions of particles across gigaparsec scales to ensure that rare structures like Booties are captured. For the future, theoretical models will continue to refine their predictions as observational data improve. Upcoming surveys will provide larger void catalogues with detailed measurements of their shapes, sizes, and dynamics. These will allow for more precise comparisons to simulations, testing LCDM and its alternatives at new levels. Boots will remain a benchmark, a structure so large that it pushes models to their limits. Its role will be to confirm or challenge the physics that underlies our understanding of the universe. Theories can predict voids and explain them, but it's the act of mapping and confirming their presence that grounds those predictions in reality. The Booties void, as extreme as it is, has inspired observational campaigns that push instruments to their limits, turning faint light from distant galaxies into data points that test the deepest models of cosmology. When the Booties void was first charted, its sheer size made it stand out so strongly that many wondered whether it was unique. For a time, it was even called the Great Nothing, as if there might not be another like it anywhere else. But as surveys expanded and astronomers mapped more of the universe, it became clear that Boots, while exceptional, is not alone. The cosmic web is filled with voids of all sizes, and some of them approach or even rival Boots in scale. By comparing these gigantic cavities, scientists gain perspective on whether Boots is truly an outlier or part of a broader pattern that tells us something fundamental about structure formation. The largest voids are often called supervoids, enormous regions spanning hundreds of millions of light years with significantly lower galaxy density than average. Booty is among the most famous because it was discovered early, but surveys such as the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recent wide-field projects have revealed many others. Each one has its own dimensions, boundaries, and degree of emptiness. Studying them as a population helps astronomers understand the statistics of voids, their frequency, and their role in testing cosmological models. One well-known example is the Eridanus supervoid. It came to prominence because it coincides with a large cold spot in the cosmic microwave background, one of the most puzzling anomalies in cosmology. The Eridanus supervoid is estimated to be about 500 million light-years across, even larger than Booties in linear dimension, though its density contrast is not as extreme. Some studies suggest that its size and location may contribute to the microwave background cold spot through the integrated Sachs-Wolf effect, though whether it can fully explain the anomaly is debated. Still, the Eridanus void highlights how supervoids are not only structural features but also potential links to cosmic background anomalies, tying local emptiness to the oldest light in the universe. Another notable void is the KBC void, named after Keenan, Barger and Cowie, the researchers who described it. This void is unusual because we may actually live inside it, or at least on its edge. The KBC void is estimated to be around 2 billion light-years in diameter, dwarfing Booties, though its underdensity is shallower. If confirmed, its existence would have profound implications. Living inside a large void could subtly affect measurements of cosmic expansion, complicating the determination of the Hubble constant. Some cosmologists have proposed that the apparent tension between local and early universe measurements of the Hubble constant might partly reflect our location within such a void. While this remains debated, the KBC void shows how voids can directly influence the interpretation of cosmological data, not just as background features but as environments we inhabit. The Hercules Corona Borealis Great Wall, while technically a wall rather than a void, helps illustrate the scale of cosmic structures. It is one of the largest known arrangements of galaxies, stretching over 10 billion light-years. Its presence implies that correspondingly vast voids must exist alongside it, since walls and voids form together. These enormous contrasts push the limits of what simulations predict. Bootes sits within this spectrum as a particularly clean spherical void, easier to identify than some of the more irregular supervoids. Other voids catalogued in surveys include the Sculptor void, the Microscopium void, and numerous others spread across the sky. Each is mapped by tracing the absence of galaxies in redshift space, revealing spherical or irregular cavities in the distribution. Many are smaller than Bootes, on the order of tens of megaparsecs, but when considered as a population, they dominate the volume of the universe. In fact, voids collectively occupy more than half of all cosmic space, though galaxies and matter concentrate in the remaining half. The Bootes void is significant not because voids are rare, but because it represents the extreme end of the distribution. Comparisons between Bootes and other giant voids also shed light on how environment influences galaxy populations. In most voids, the galaxies that do exist share similar traits. They are smaller, more gas-rich, and actively forming stars, but the details vary depending on the void's size, shape, and depth. In shallower voids, there may be more substructure, with tendrils of galaxies threading through. In deeper ones, like Bootes, galaxies are sparser and more isolated. These differences help refine theories of galaxy evolution, showing how environment modulates outcomes across a spectrum of conditions. The statistical study of voids has become a discipline of its own, often called void cosmology. Researchers compile catalogues of voids from surveys and measure their properties: size distributions, density contrasts, ellipticities, and alignments. These properties can be compared to simulations to test cosmological models. Bootes and other supervoids anchor the high end of these distributions, providing critical data points. Without them, models might underestimate the extremes of cosmic structure. With them, models gain confirmation that even the most unusual features can be explained by the same physics that governs the rest of the universe. One of the ongoing debates in cosmology is whether supervoids like Bootes and Eridanus are consistent with the expected statistics of LCDM, or whether they hint at new physics. Most evidence suggests consistency, but the rarity of such structures means that each new discovery attracts scrutiny. If voids larger than predicted are found in significant numbers, it could challenge assumptions about the initial conditions of the universe, or the nature of dark matter and dark energy. For now, Bootes remains within the expected range, but it is close enough to the edge to keep theorists cautious. It is also worth noting that voids are not isolated objects. They connect and overlap, forming a complex network of cavities that interlock with filaments. The Bootes void may appear as a distinct bubble, but in reality, its boundaries blend into surrounding structures. Other voids have similar relationships, merging into larger underdense regions or touching the edges of galaxy walls. Mapping these connections is part of the challenge of void cosmology. It requires careful definitions. Where does one void end and another begin? Different algorithms produce slightly different catalogues, but the largest voids consistently appear, confirming their reality. As instruments improve, astronomers are beginning to identify voids not only in the nearby universe, but also at higher redshifts, looking billions of years into the past. These younger voids are smaller because structure has not had as much time to grow, but they evolve into the giants we see today. Tracing this growth provides another way to test cosmology. Bootes represents a mature void at low redshift, while high redshift surveys show its predecessors in earlier stages. Comparing them across time allows scientists to see how voids expand, round out, and sharpen their boundaries under the influence of cosmic expansion and dark energy. From a broader perspective, the existence of multiple giant voids emphasizes that the cosmic web is a balance of contrasts. Filaments and clusters stand out because voids surround them. Walls appear enormous because emptiness defines their edges. Bootes may be the poster child of cosmic emptiness, but Eridanus, KBC, and countless smaller voids all contribute to the same pattern. Together they confirm that the universe is not uniformly filled, but shaped by alternating regions of presence and absence, matter and near nothing. The comparison of Bootes to other gigantic voids also reminds us that our understanding is incomplete. Each new survey extends the map, revealing voids we did not know existed. The cosmic web continues beyond what we have charted, and there may be voids larger than any yet observed. Bootes holds the record for fame, but in the vastness of the universe, there may be structures that dwarf even it, waiting to be discovered. When astronomers first charted the Bootes void, one of the immediate questions was not just how large it was, but how unusual it might be. Was this an extraordinary fluke in the cosmic landscape, or simply one extreme case in a natural spectrum of structures? To answer that requires a statistical perspective, because in cosmology we rarely talk about single objects in isolation. Instead, we consider populations, distributions, and probabilities. The Bootes void became not only a striking discovery, but also a challenge to quantify just how rare such an emptiness should be in the universe we understand. The starting point for thinking about rarity is the initial spectrum of density fluctuations imprinted in the early universe. Inflation-generated, nearly scale-invariant Gaussian fluctuations, tiny variations in density, randomly distributed but with well-defined statistical properties. From those fluctuations grew all the structure we see today. The mathematics of Gaussian statistics tells us how likely different amplitudes of fluctuation are. Most regions were close to average density, some a little above, some a little below, and a very few far from the mean. Bootes represents one of those extreme deviations, a region that began with a density lower than most, and which cosmic expansion amplified into a vast void. To determine whether such a void is surprising, cosmologists turn to simulations. By evolving billions of particles under gravity from inflationary initial conditions, these simulations reproduce the cosmic web. Within the simulated universe, voids naturally emerge. By cataloguing their sizes and distributions, scientists can measure how common voids of various dimensions should be. What these simulations show is that voids are ubiquitous. They occupy most of the volume of the universe, but most are modest in size, tens of megaparsecs across. As the scale increases, the number of voids falls rapidly. A void the size of Bootes is rare, but not impossible. In fact, simulations predict that the observable universe should contain a handful of voids of comparable size. The existence of Bootes fits within this prediction, making it a rare but expected structure. The concept of rarity in this context is statistical rather than absolute. Just as rolling dice can occasionally yield unusual sequences, the random nature of initial fluctuations means that large voids can appear, even if they are uncommon. The Bootes void is one of those unlikely outcomes. Its presence does not break the rules but illustrates them. It is an extreme value in the distribution, a tail event, but one that falls within the probabilities defined by the standard model. To quantify this more precisely, cosmologists often use the void size function, an analogue to the mass function for clusters. This function describes how many voids of a given radius are expected per unit volume. It falls off steeply at large sizes, meaning that the number of giant voids is small. By comparing observed void catalogues to this function, scientists can test cosmological parameters. If too many large voids are observed, it might suggest different values of S8, the parameter that measures the amplitude of fluctuations, or the density of matter. The Bootes void, by fitting near the tail of the distribution, provides an important check. Its existence is consistent with current values, which strengthens confidence in the model. It is also useful to compare Bootes to other rare structures. In clusters, we have the Coma cluster, the Virgo cluster, and other massive aggregations of galaxies. In walls, we have the Sloan Great Wall and the Hercules Corona Borealis Great Wall. These too are statistical extremes, rare but not impossible. Bootes belongs to this family of extremes. Together they show that the universe produces structures across a wide range, from the smallest dwarfs to the largest voids, each with its place in the statistical spectrum. The rarity of Bootes also raises questions about perception. Because it is so large, it draws attention, but statistically the universe is filled with voids. In fact, voids occupy more volume than filaments and clusters combined. What makes Bootes stand out is not that it is unique, but that it is one of the few voids so large and clean that it can be easily recognised. Many voids are irregular, overlapping or shallow, making them less striking. Bootes, with its nearly spherical shape and pronounced emptiness, is easier to identify. In this sense, it is both a statistical outlier and a perceptual standout. Another aspect of rarity involves how Bootes influences measurements of the large-scale universe. Because voids expand faster than average, they can bias certain observations if not accounted for. For example, the apparent brightness of galaxies or supernova seen through voids can be affected by gravitational lensing. The integrated Sachs-Wolf effect adds subtle signals to the cosmic microwave background. If Bootes were more common, these effects could distort cosmological measurements. The fact that Bootes is rare means that its influence is limited, but it also provides an opportunity. By studying it in detail, astronomers can better understand how voids as a population affect observations. It is also worth considering how rarity is defined in human terms. To us, a void 330 million light-years across sounds inconceivably large, and therefore special. But in the scale of the universe, which is 93 billion light-years across, Bootes is still a fraction. From a statistical perspective, its rarity is relative, not absolute. There are larger voids, like the KBC void, albeit shallower. There are deeper voids, though smaller. Bootes sits at a point in this multidimensional spectrum that happens to maximize both size and depth, making it prominent. But it is part of a continuum, not a singular anomaly. The study of rarity also ties into the question of cosmic variance. Because we observe only one universe, our sample size is limited. Even if Bootes is rare, it may not be surprising that we happen to see one, given the vast number of voids available. This limitation reminds us that probability in cosmology is different from probability in controlled experiments. We cannot rerun the universe, but we can use simulations to understand what is typical and what is unusual. In that framework, Bootes is unusual but not impossible, reinforcing that our universe behaves statistically as expected. Looking ahead, as surveys expand, we will likely find more voids comparable to Bootes. Each discovery will refine our understanding of rarity. Perhaps Bootes will remain one of the largest, or perhaps we will find even larger examples. Either way, the statistical distribution of voids will become clearer. This will help constrain cosmological parameters more tightly, improving our knowledge of dark matter, dark energy, and initial conditions. Bootes has already played this role by showing that rare extremes exist, pushing models to account for them. Future voids will continue this process. From a broader perspective, the concept of rarity emphasizes how cosmology blends chance and necessity. The laws of physics set the rules, but randomness in initial conditions determines outcomes. Bootes is a product of both. The rules of inflation and gravity created the conditions, and chance determined that one region would be unusually underdense. Its rarity is therefore not a mystery but a reflection of the probabilistic nature of the universe. When we look at the Boots void and ask how it came to be, we are really asking about the process by which the universe transforms from near uniformity to complexity. At the time of the cosmic microwave background, the distribution of matter was astonishingly smooth. The density variations were at the level of 1 part in 100,000, and yet today the universe contains galaxies, clusters, filaments, and vast voids like booties stretching across hundreds of millions of light years. The physics of structure growth explains this transformation, showing how gravity amplifies small fluctuations into large-scale patterns. The first ingredient in this growth is the initial spectrum of fluctuations seeded during cosmic inflation. These fluctuations were random, Gaussian, and nearly scale invariant, meaning that density differences occurred across a wide range of scales with similar amplitude. They were imprinted in the distribution of both dark matter and baryons. When inflation ended, the universe entered a hot, dense phase dominated by radiation, and the fluctuations began to evolve under the competing influences of pressure, expansion, and gravity. In the radiation-dominated era, before the universe was about 47,000 years old, radiation pressure resisted the growth of fluctuations in baryonic matter. Any attempt for matter to clump was countered by the pressure of photons coupled to the plasma. This led to oscillations known as baryon acoustic oscillations, which left subtle imprints in both the cosmic microwave background and the distribution of galaxies today. Dark matter, however, did not interact with radiation in the same way. It was free to begin clumping earlier, forming the gravitational wells into which baryons would later fall. This distinction between baryons and dark matter is central to structure growth, because it means that dark matter provided the scaffolding on which galaxies and filaments formed. Once the universe cooled enough for matter and radiation to decouple, about 380,000 years after the Big Bang, baryons were free to fall into the dark matter potential wells. From that point onward, fluctuations could grow more efficiently. Gravity pulled matter toward overdense regions, while underdense regions lost matter. This process is known as gravitational instability. It is inherently nonlinear. Small differences grow larger over time, creating ever stronger contrasts. The Bootes void began as a region slightly underdense compared to its surroundings, and over billions of years matter flowed outward, leaving behind the vast emptiness we see today. In the linear regime, when density contrasts are small, the growth of structure can be described by relatively simple equations. The growth rate depends on the expansion of the universe, which in turn depends on the density of matter, radiation, and dark energy. During the matter-dominated era, growth was efficient, with density contrasts increasing steadily. During the radiation-dominated era, growth was suppressed. Once dark energy began to dominate a few billion years ago, growth slowed again, because accelerated expansion counteracts gravitational clumping. This interplay defines the timeline of structure growth, suppressed at first, strong for billions of years, and then slowed again. As contrasts grow larger, however, the linear approximation breaks down. Overdense regions collapse into non-linear structures such as galaxies and clusters. Underdense regions expand into non-linear voids. The physics becomes more complex, requiring numerical simulations to follow the detailed evolution. These simulations, starting from initial conditions consistent with the microwave background, reproduce the cosmic web remarkably well. They show filaments forming at the intersections of sheets of matter, clusters forming at the nodes, and voids expanding between them. The Bootes void is one such outcome, its properties reflecting the physics of gravitational instability and cosmic expansion working together over billions of years. The mathematics of nonlinear growth reveals some important features of voids. One is that they tend to become more spherical over time, even if they began irregular. This happens because expansion smooths out differences in direction. Another is that voids expand faster than the background universe, since their lower density means less gravitational resistance. This explains why Boots is not just empty, but unusually large. Its initial underdensity, once amplified by billions of years of preferential expansion, became a bubble of hundreds of millions of light years. Another crucial aspect of structure growth is the role of mergers and interactions. In overdense regions, small halos of dark matter merge into larger halos, creating a hierarchy of structures. This is known as hierarchical clustering. In voids, the process works in reverse. Small underdensities merge into larger underdensities, carving out bigger voids from the cosmic web. The Boots void is an example of such merging. Smaller voids coalesced into a single giant cavity, surrounded by walls of galaxies where matter accumulated. This merging process continues today, as voids grow and combine, shaping the overall distribution of matter. The growth of structure also involves feedback from astrophysical processes. Supernovae, stellar winds, and active galactic nuclei inject energy into their surroundings, influencing how gas cools and forms stars. While these processes are critical on galaxy scales, their influence on voids is limited. The Bootes void is shaped primarily by gravity and expansion, not by feedback. Its few galaxies may evolve differently because of their isolation, but the void itself is defined by large-scale physics. Another point of connection between structure growth and voids is the role of dark energy. Accelerated expansion slows the growth of new structures while enhancing the expansion of voids. This means that voids are particularly sensitive indicators of dark energy. The rate at which they grow and their present sizes reflect the balance between matter and dark energy. The Bootes void, being so large, provides an extreme test of this balance. Its very existence confirms that the combination of initial fluctuations, dark matter scaffolding, and dark energy-driven expansion can produce structures on this scale. Statistical measures of structure growth, such as the matter, power spectrum and correlation functions, include contributions from voids. On large scales, voids reduce clustering by providing empty regions where galaxies are less likely to be found. On small scales, overdense regions dominate. The combined signal reflects the full cosmic web. By comparing observed power spectra to theoretical predictions, cosmologists test whether the growth of structure matches expectations. So far, the match is strong, with voids like Bootes falling naturally within the predictions. It is also important to consider that structure growth is scale-dependent. Small-scale fluctuations grow faster than large-scale ones, because gravity can act more efficiently over shorter distances. This explains why galaxies and clusters formed earlier than voids. By the time the universe was only a few billion years old, galaxies had already formed, while voids were still developing. Over time, the large-scale underdensities caught up, creating the vast cavities we see today. The Bootes void is a mature void, fully developed after billions of years, but its roots stretch back to those early times when small fluctuations began to grow. The physics of structure growth also highlights the interconnectedness of the cosmic web. Voids do not exist in isolation. Their expansion pushes matter into surrounding filaments, which grow denser in response. The Bootes void is bounded by walls of galaxies precisely because its emptiness forced matter outward. This mutual reinforcement means that voids and filaments are two sides of the same process. The growth of one shapes the growth of the other, producing the sponge-like pattern of the universe. For Bootes specifically, its statistical rarity makes it an excellent case study of extreme structure growth. By examining how such a large void can arise, cosmologists test whether our theories handle the tails of the distribution correctly. The fact that Bootes can be reproduced in simulations gives confidence that the physics is sound. At the same time, its extreme scale ensures that it remains a focus of study, because rare events are often the best probes of fundamental laws. Looking forward, the physics of structure growth will continue to be tested by upcoming surveys. Instruments like the Dark Energy Spectroscopic Instrument and the Euclid mission will map billions of galaxies, providing more detailed measurements of voids. These data will refine our understanding of how fluctuations grow, how voids expand, and how dark energy influences structure. The Bootis void will remain a benchmark in this effort, a giant cavity that pushes models to their limits and ensures that our theories account for the rare as well as the common. The Bootis void sits as one of the largest holes in the observable universe, a cavern of emptiness stretching more than 300 million light-years across. Within the standard cosmological model, its existence is a natural, though rare, outcome of gravitational instability acting on the nearly uniform conditions seeded during inflation. Yet, whenever a structure pushes the boundaries of expectation, scientists ask whether it might hint at something deeper, something beyond the prevailing framework. Alternative cosmologies, whether modifications to gravity, changes in the properties of dark matter, or more radical departures from standard physics, often find their testing ground in places like Bootis. Emptiness, in this sense, becomes a stage for the most speculative ideas about the nature of reality. The standard model of cosmology, often summarized as LCDM, rests on a few pillars: cold, collisionless dark matter that clumps under gravity, dark energy in the form of a cosmological constant, driving accelerated expansion, and general relativity as the law of gravity on all scales. With these ingredients, simulations produce a universe that matches observations remarkably well. The distribution of galaxies, the statistics of the cosmic microwave background, the growth of structure, and the sizes of voids all fall into place. But the model leaves fundamental questions unanswered. We do not know what dark matter is, only that it must exist. We do not know what dark energy is, only that it accelerates expansion. These gaps leave room for alternatives, and voids like Bootis are prime places to test them. One class of alternatives involves modifying gravity itself. General relativity has been tested extensively within the solar system and in the dynamics of binary pulsars, but its validity on cosmic scales remains less directly confirmed. Some models, such as EFR, gravity, or scalar tensor theories, attempt to adjust Einstein's equations in ways that could mimic dark energy or alter structure formation. These modifications often predict different behaviors for voids. In some cases, voids expand faster than in general relativity, because the effective strength of gravity is reduced in underdense regions. In others, additional fields mediate long-range forces, changing how matter flows out of voids. By measuring the velocity fields around Bootis and similar structures, cosmologists can test whether gravity behaves exactly as expected or shows deviations. So far, the evidence supports general relativity, but Bootis remains an important case because its extreme size makes even small deviations easier to detect. Another alternative focuses on the nature of dark matter. In the standard model, dark matter is cold, meaning its particles move slowly compared to the speed of light, and collisionless, meaning they interact only gravitationally. This allows small-scale fluctuations to grow, producing galaxies and substructure. But if dark matter were warm, with particles moving fast enough to erase small-scale fluctuations, the distribution of galaxies would be smoother. Voids might contain fewer small galaxies, making them emptier. If dark matter were self-interacting, colliding with itself through unknown forces, void dynamics might also differ, because halos would form differently. Boots provides a natural test of these ideas. By examining whether galaxies inside it match the predictions of cold dark matter, astronomers can constrain alternatives. The presence of small gas-rich galaxies within Bootis supports the cold dark matter picture, but the debate remains open, and future observations may refine the picture. Some theories go even further, suggesting that dark energy is not a cosmological constant, but a dynamic field that evolves over time. These quintessence models predict that the influence of dark energy changes with redshift, which in turn alters the growth rate of voids. In such models, boots may have expanded differently in the past compared to what LCDM predicts. Measuring the exact density profile of boots, how sharply it transitions from emptiness to filament walls, can provide tests of these models. If the profile is steeper or shallower than expected, it might indicate new physics in dark energy. There are also speculative ideas that place voids at the center of explanations for cosmic acceleration. Some inhomogeneous cosmologies propose that if we live near the center of a gigantic void, the apparent acceleration of the universe could be an illusion caused by our position. Light traveling through regions of different density would create observational effects that mimic dark energy. These models, sometimes called Lemaitre-Tolman-Bondi cosmologies, have been largely disfavored because they require fine-tuned positions and struggle to match all observations. But they illustrate the role voids can play in challenging assumptions. The KBC void, if confirmed, briefly revives such discussions, though the consensus remains that dark energy is real, and not simply an artifact of inhomogeneity. Booties, while not our home, adds weight to these considerations by showing just how large voids can be, making the idea at least conceivable enough to test. Another intriguing possibility arises from theories that connect voids to the multiverse. In some inflationary scenarios, inflation never completely ends but continues in different regions, creating multiple bubble universes with different properties. Collisions or interactions between such bubbles could, in principle, leave imprints on the large-scale structure of our universe. Some speculative papers have suggested that unusually large voids could be relics of such processes, scars left by interactions beyond our observable horizon. Bootes, with its dramatic emptiness, naturally attracts this speculation, while there is no solid evidence that it is anything more than a statistical fluctuation. The fact that it invites such discussion shows how voids capture the imagination of theorists. Even within the standard framework, there are unresolved tensions that motivate alternative thinking. One example is the discrepancy between local and early universe measurements of the Hubble constant. Some have argued that large voids could play a role in this tension by biasing local measurements. If we happen to sit inside a relatively underdense region, the expansion we measure locally could be faster than the global average. While the Bootes void is too distant to explain this directly, the KBC void and others closer to us are part of the discussion. The general point is that voids remind us that the universe is not uniform, and any alternative cosmology must account for the effects of inhomogeneity on observations. The challenge with alternative cosmologies is that they must match not only the existence of voids like Bootes, but also the entire suite of cosmological observations. The cosmic microwave background, galaxy clustering, lensing, baryon acoustic oscillations and supernova distances all provide constraints. Bootes by itself cannot overturn LCDM, but it adds to the cumulative evidence. Any alternative must reproduce not only typical voids, but also rare ones, not only average clustering but also extremes. In this way, Bootes acts as a stress test, pushing models to account for the larger structures the universe produces. For now, the weight of evidence favours the standard model. Simulations under LCDM reproduce Bootes and predict that such voids, while rare, should exist. Alternative models may tweak the details, but none has yet provided a compelling reason to discard the standard framework. Still, the openness of cosmology to alternatives is a strength, not a weakness. Bootes remains a reminder that our understanding is provisional, built on the best evidence available but always subject to challenge. Its vast emptiness ensures that it will remain a natural target for those seeking to test the boundaries of theory. As observations improve, the ability to discriminate between models will increase. Mapping the velocity flows around Bootes, measuring its lensing imprint, and identifying the properties of its galaxies all provide data points that can distinguish between cold and warm dark matter, constant and dynamic dark energy, standard and modified gravity. Each of these alternatives leaves subtle fingerprints in voids, magnified by their sensitivity to cosmic expansion. Boots is therefore not only a curiosity but a laboratory for the deepest questions of cosmology. When the Boots void was first announced in the early 1980s, the scientific community reacted with a mix of fascination and skepticism. How could such a vast emptiness exist, stretching hundreds of millions of light-years across, containing so few galaxies when theory predicted that the cosmos should be relatively uniform? The discovery was based on early redshift surveys, which were limited by the technology of the time. Telescopes could record spectra for only a handful of galaxies at once, and distances were painstakingly measured one by one. To map even a small region of space took years of effort. The Bootes void stood out dramatically, but verifying its properties required years of additional work. This highlights the first and most fundamental challenge of studying voids. They are defined not by what is present, but by what is absent. Detecting absence requires a complete and accurate map, which is never easy to obtain. The basic difficulty is that galaxies are the traces of the underlying structure. To find a void, astronomers must identify regions where galaxies are scarce. But galaxies are not distributed evenly, and surveys are always incomplete. A patch of sky with fewer measured galaxies might reflect a true underdensity, or it might simply reflect observational limits. Distinguishing between the two requires deep, uniform surveys that can detect even faint galaxies. Early surveys lacked this depth, which is why some initially questioned whether the Bootes void was truly as empty as it seemed. As technology improved, with instruments capable of measuring thousands of redshifts simultaneously, the reality of the void became clearer. But even today, defining its exact boundaries requires careful statistical treatment. Another challenge lies in the definition of a void itself. What counts as empty? Different algorithms for identifying voids can produce different results. Some define voids as regions where the density falls below a certain threshold. Others use geometrical methods, drawing spheres around underdense areas. Still others trace the watershed lines of density fields, dividing space into basins of emptiness. Each method has strengths and weaknesses, and each can yield slightly different catalogues of voids. For Bootes, its size and stark contrast make it robust against these differences, but for smaller voids, the choice of method matters a great deal. This illustrates the difficulty of comparing observations to theory. The definition of a void must be consistent across both. Even once voids are identified, measuring their properties presents further hurdles. Distances in astronomy are not measured directly but inferred through redshifts. Galaxies emit light that is stretched by the expansion of the universe, and the degree of stretching reveals their distance. But peculiar velocities, the motions of galaxies relative to the Hubble flow, distort these measurements. In clusters, galaxies may move toward or away from us due to local gravity, creating the so-called finger of God effect in redshift space. In voids, outflows can create the opposite effect, flattening structures along the line of sight. These redshift space distortions complicate the task of measuring void sizes and shapes. Correcting for them requires careful modelling, and uncertainties remain. Another observational difficulty is sensitivity. Voids are filled mostly with faint small galaxies, often dwarfs that are difficult to detect. These galaxies may contribute significantly to the overall density, but if surveys miss them, the void may appear emptier than it truly is. Detecting these faint galaxies requires deep imaging and spectroscopy, which consume large amounts of telescope time. In the Bootes void, only a few dozen galaxies are known, but there may be more lurking below detection thresholds. Future surveys with more sensitive instruments may reveal them, refining our picture of just how empty Bootes really is. Instrumental limitations also play a role. Wide-field surveys must balance depth with area. Mapping a large volume requires covering wide swathes of sky, but mapping faint galaxies requires long exposures. Achieving both is challenging. Surveys like the Sloan Digital Sky Survey made enormous progress, cataloguing millions of galaxies across a large fraction of the sky. But even SDSS had limits, particularly at higher redshifts where galaxies become too faint. The Bootes void lies at a distance where these limits begin to matter, making it an ongoing challenge to map its full extent. Upcoming surveys, such as those conducted by the Dark Energy Spectroscopic Instrument and the Vera C. Rubin Observatory, promise to push beyond these limits, providing deeper and more complete maps. Another subtle challenge is cosmic variance. The universe is only one realization of a statistical process. Even if our models predict a certain distribution of voids, the actual universe may deviate simply due to chance. Bootes may be one such deviation, an unusually large void in our particular patch of cosmos. Distinguishing between statistical fluctuations and new physics requires large samples of voids, not just one. This is why cosmologists build void catalogues from surveys, comparing their statistical properties to simulations. Bootes remains important as an extreme case, but it must be seen in the context of the broader distribution. Observations are also limited by the difficulty of probing dark matter directly. Galaxies trace the luminous matter, but dark matter dominates the mass. Voids are defined by both, yet we see only the light. Gravitational lensing offers a way to measure dark matter directly, but in voids, the effect is weak. Detecting it requires stacking many voids together, averaging their signals. Bootes may be large enough to show an individual signal, but even then the measurements are at the edge of detectability. This makes it challenging to confirm that voids are truly underdense in total mass, though the evidence from lensing so far supports the picture. Another observational challenge involves connecting voids to the cosmic microwave background. As photons from the CMB pass through voids, they experience the integrated Sachs-Wolf effect, but the signal is minuscule. Detecting it requires cross-correlating maps of the microwave background with void catalogues. The results show consistency, but noise remains high. Bootes should contribute a strong signal, but isolating it against the background fluctuations is extremely difficult. This highlights a recurring theme. The most interesting effects of voids are often the hardest to measure, buried beneath larger signals from other processes. The observational study of voids also intersects with practical limitations of telescope time and resources. Mapping galaxies across billions of light-years requires long exposures, large instruments, and years of work. Competing demands from other fields, planetary science, stellar astrophysics, exoplanet searches, limit the time available. Large collaborations are needed to gather the data, process it, and make it publicly available. The Bootes void, despite its fame, is only one target among many, and its study competes with countless other cosmic questions. Even when surveys succeed, interpreting the data requires caution. Systematic errors can creep in through calibration, photometric uncertainties, or incompleteness in redshift catalogues. A missed population of galaxies could bias the measured density. An error in redshift calibration could distort the apparent size. Careful cross-checks are essential. Bootes has withstood these checks, remaining one of the largest known voids, but its exact properties remain subject to refinement as data improve. Finally, there is the challenge of communication. Voids capture public imagination because they are described as great holes in the universe, regions of nothingness. But scientifically, they are subtle, defined not by absolute absence but by relative scarcity. Explaining this distinction requires careful language. Bootes is not perfectly empty. It contains galaxies, dark matter, and gas. Its significance lies not in absolute void, but in statistical underdensity. Conveying this nuance is part of the challenge of observational cosmology, balancing accuracy with accessibility. These challenges do not diminish the importance of voids. Rather, they highlight why their study requires persistence and innovation. Bootes remains a benchmark case, inspiring new surveys, new methods, and new ways of thinking about absence as data. Each improvement in observational capability brings the void into sharper focus, revealing more about how emptiness shapes the universe. When we call the Buddha's void a hole in the universe, we invite a question that is as philosophical as it is scientific. What does it mean for something to be nothing? In ordinary language, a void suggests absence, an empty space devoid of content. But physics rarely accepts a simple definition of nothing. Even the largest voids in the cosmos, even the Buddha's void stretching over 300 million light-years, are not absolute vacuums. They contain galaxies, sparse and isolated though they may be. They contain dark matter, invisible but influential. They contain radiation crossing unhindered, virtual particles flickering in and out of existence, and the ever-present stretching of space itself. To understand the meaning of nothing in this context, we must disentangle how physics defines emptiness, how cosmology uses the word void, and how the human mind interprets absence. At its most basic, the Buddha's void is an underdense region. Compared to the average number of galaxies per unit volume, it contains far fewer. Statistically, where there should be thousands of galaxies, only a few dozen exist. This is enough for astronomers to label it a void, but it is not enough to call it nothing. On the scale of the cosmos, nothingness does not exist in the absolute sense. Even in intergalactic space, there are atoms drifting, photons moving, dark matter, halos extending, and quantum fields seething. Emptiness in physics is always relative, never absolute. The Buddha's void is therefore a lesson in the relativity of nothing. It is not the absence of everything, but the absence of what we expected. This distinction matters because it shapes how cosmology interprets the universe. If Buddha were truly nothing, a literal hole in space, it would contradict the continuity of physics. Instead, it is part of the fabric of the cosmic web, an underdense patch connected to overdense filaments. Matter has flowed out of it over billions of years, but space itself remains, expanding and evolving. Nothing in physics does not mean non-existence. It means lower density, lower content, a quieter stage. The Buddha's void embodies this interpretation, a physical reminder that absence can be defined and studied as carefully as presence. From another angle, the concept of nothing in cosmology links to the vacuum of quantum field theory. Even what we think of as empty space is filled with activity. Virtual particles appear and vanish. Fields fluctuate and energy pervades even in the absence of matter. This quantum vacuum is not the nothing of philosophy, but a physical state with properties. It contributes to the cosmological constant, the energy density of empty space that we observe as dark energy. In this sense, voids like Buddha's are not devoid of content but are saturated with the most fundamental kind of something, the energy of space itself. The meaning of nothing also changes depending on scale. To a galaxy cluster, Buddha's is nearly empty, because its density is negligible compared to that of a cluster core. To an atom, Buddha's is inconceivably full, because trillions upon trillions of atoms spread thinly still populate its expanse. To human imagination, Buddha's is incomprehensible, because it combines vastness with scarcity in a way that defies intuition. The meaning of nothing, then, depends not only on physics but on perspective. What seems like emptiness from one angle is crowded from another. When astronomers describe Buddha's to the public, they often call it the largest hole in the universe. This captures attention, but it risks misunderstanding. It is not a hole in the fabric of space. It is a feature of the cosmic distribution of matter, a region where galaxies are sparse. Calling it nothing is metaphorical, a way of conveying scale and contrast. Scientifically, it is defined by measurable properties: density, contrast, volume, shape, galaxy population. These make it something, even if that something is less than expected. The meaning of nothing here is that it is not truly empty but emptier than average, and that difference itself becomes data. For cosmologists, the lesson of voids is that nothingness is an active participant in the universe. Emptiness influences motion, shapes flows of matter, and expands faster than crowded regions. The Bootes void is not inert. Its gravitational effects push galaxies outward, its expansion contributes to cosmic flows, its presence alters the path of photons. In physics, even nothing does something. The meaning of nothing is therefore inseparable from dynamics. Voids remind us that absence is never passive. This leads to a deeper connection, the role of nothing in the long-term fate of the universe. As dark energy drives accelerated expansion, voids will grow larger, filaments will thin, and galaxies will retreat from one another. Over trillions of years, emptiness will dominate. The Bootes void is a preview of this cosmic future, where nothingness defines the landscape. In that distant time, galaxies will live in isolation, surrounded by vast voids, with little evidence that others ever existed. Nothing will become the default state. The meaning of nothing will shift again, from relative rarity to overwhelming normality. Philosophically, this resonates with the ancient human struggle to understand emptiness. Cultures have long debated whether nothing can exist, whether absence is real, or simply the lack of presence. Physics offers a pragmatic answer. Nothing is always something in disguise. The Bootes void shows us that emptiness can be mapped, measured, and explained. It is not a philosophical void, but a physical one, structured by equations, shaped by forces, and filled with subtle traces of matter and energy. The meaning of nothing, in this light, is that it is part of everything, one half of the contrast that makes the universe comprehensible. There is also a human dimension to this. When we contemplate Bootes, we feel the enormity of scale and the strangeness of a space so vast and so empty. It challenges intuition, forcing us to think beyond everyday concepts. Nothing becomes a window into the unknown, a way of touching the limits of imagination. For scientists, it is a data set. For the rest of us, it is an invitation to reflect on what it means to live in a universe where emptiness is as real and as structured as presence. In physics, nothing is never absolute, but it is always meaningful. The Bootes void is not a hole in the universe, but a structure in its own right. Its existence tells us about inflation, dark matter, dark energy, and the growth of cosmic structure. Its emptiness is not absence, but information. To call it nothing is to acknowledge its scarcity, but to study it is to realize its richness. The meaning of nothing is that even absence can reveal the deepest truths of physics, and as the universe continues to expand, the role of nothing will only grow. Voids will stretch, galaxies will fade from view, and emptiness will define the cosmic horizon. The Bootes void is not an exception, but a foreshadowing. It shows us not only what the universe contains, but what it is becoming. Nothing in the end is not the opposite of something. It is the stage on which everything plays out, and in cosmology, it is as real, as measurable, and as revealing as the galaxies themselves. When we reach the end of a journey through something as vast as the Bootes void, it can feel like we have travelled outward across unimaginable distances, yet at the same time inward into the structures that frame our own sense of place. The Bootes void is more than an astronomical object. It is a way of seeing how the universe arranges itself, how the smallest fluctuations in its earliest moments grow into the largest features of space. By following this emptiness across physics, surveys, theories, and imagination, we learn not only what is missing, but also what remains. It is tempting to think of an ending here, to close the book on Bootes as if we now understand it fully. But astronomy rarely offers closure in that way. Each answer points to more questions. The Bootes void has shown us how emptiness interacts with dark energy, how gravity shapes even regions that appear passive, how galaxies evolve in solitude, and how initial conditions become sculpted across cosmic time. And yet, what exactly dark matter is, what dark energy truly represents, and whether voids hide deeper surprises remain open questions. The Bootes void is therefore not a conclusion but an ongoing part of discovery, always waiting to be reinterpreted as science advances. As we reflect on the Bootes void, it becomes clear that its emptiness is as valuable as any cluster's richness. The galaxies that string together into filaments gain their meaning from contrast with what surrounds them. Without voids, the web of the universe would not exist in the same way. Without Bootes and other supervoids, the statistics of cosmic structure would be incomplete. Nothingness is not absence but architecture, shaping what is present by providing the spaces in between. The study of voids has also shown us how fragile human concepts of emptiness can be. To our senses, emptiness is a vacuum, a place stripped of content. To physics, emptiness is a spectrum. On one level, Bootes is nearly empty, hundreds of millions of light years with barely a few dozen galaxies. On another, it is full of gas, dark matter, radiation, and the restless background of quantum fields. This layered concept of nothing reveals how far physics has taken us from ordinary language, forcing us to refine ideas that once felt simple. The Bootes void invites us to think differently about what it means for space to be full or empty. In practical terms, Bootes has inspired a generation of observations. Its discovery in the early redshift surveys of the 1980s demonstrated the power of mapping the three-dimensional universe. Its confirmation in later surveys validated both technique and theory. Today, it remains a benchmark for new projects. When scientists plan instruments to measure voids or test dark energy, Bootes often appears in the conversation as an extreme case that helps calibrate expectations. It has moved from being a surprise to being a standard, from anomaly to data point, and that transition is part of what science always does: turn the extraordinary into the understood. But Bootes retains its power to spark reflection. To contemplate hundreds of millions of light years of near emptiness is to confront scale in a way that stretches the imagination. It reminds us that the universe is not built to human proportion. What feels immense to us is commonplace to it, and what feels empty to us is still full of subtle forces and unseen matter. The Bootes void shows us how small we are, but also how far we have come in mapping and comprehending a universe that dwarfs us. For cosmologists, Bootes represents a test of the LCDM model, and it passes. For philosophers, it represents the paradox of nothingness being something. For observers, it represents a challenge, a region difficult to measure but rewarding to study. For the rest of us, it represents a reminder that the universe is stranger, larger and more layered than our everyday intuition suggests. It is not just a hole in space. It is a story that connects quantum fluctuations to the fate of galaxies, theory to observation, emptiness to meaning. If we allow ourselves to drift with that story, the Bootes void becomes more than a physical location. It becomes a symbol of how science works. We start with curiosity, with a strange absence in a survey map. We test, we measure, we model. We connect emptiness to dark matter, dark energy, inflation and cosmic expansion. And through that process, we discover that even nothing can teach us everything. The Bootes void reminds us that knowledge is not found only where matter gathers, but also where it retreats. In the future, voids will become even more important. As surveys deepen and expand, void catalogues will grow, providing new tests of cosmology. As gravitational wave astronomy matures, even ripples in space-time may be traced through voids, testing theories in ways we cannot yet imagine. As instruments become sensitive enough to map faint dwarf galaxies in the Bootes void, our sense of its contents will sharpen, and as theoretical models evolve, Bootes will remain a standard against which to compare extremes. Its role is not to fade into history, but to continue guiding inquiry. This is the rhythm of cosmology. Every discovery, from quasars to microwave background anisotropies to the Buddha's void, first surprises, then settles into the structure of understanding. What was once shocking becomes normal. What was once an anomaly becomes a data point. What was once nothing becomes something. And so it is with Buddhas, a void that began as a curiosity and became one of the cornerstones of how we think about the universe. As we rest with the Buddha's void, we can let its scale sink in. 300 million light-years of near emptiness, a region so vast that light itself takes hundreds of millions of years to cross it. A structure seeded by fluctuations smaller than atoms, stretched by inflation, carved by gravity, and amplified by dark energy. A place that contains almost nothing, and yet reveals almost everything about how the universe works. The Buddha's void is both absence and explanation, both emptiness and insight. So we close here not with a final word, but with a quiet pause. The Buddha's void is still there, stretching silently in the sky, reminding us that the largest features of the universe are not always clusters or walls, but the spaces between them, and as the universe continues to expand, those spaces will only grow. To live in a cosmos like this is to live in a place where nothing has meaning, where emptiness speaks, and where even the greatest voids are part of the story that binds everything together.